Jaun Andreok, arratsaldeon.
Arratsaldeon eta Donosti International Physics Centerren izenean, ongi etorri Passion for Knowledge zientzia jaialdia.
Buenas tardes y bienvenidas y bienvenidos a Passion for Knowledge.
Somos Alaitz Ochoa Deribe, divulgadora de Luyar, y Javier Aizpurua, físico del Donosti International Physics Center y del Centro de Física de Materiales. Y tenemos el gusto de presentar hoy las charlas principales.
Ya es el tercer día que nos reunimos aquí en las conferencias plenarias del Victoria Eugenia y nos alegra ver que algunas personas del público repiten, ¿verdad? Nos empiezan a sonar las caras.
Sí. Y a quienes vienen por primera vez, pues les queremos contar que el objetivo de Passion for Knowledge es promocionar la ciencia como actividad cultural clave para contribuir al bienestar de las generaciones venideras. Destacar el conocimiento como motor del progreso científico, tecnológico y cultural.
Gaurko programan 3 hitzaldi nagusi izango ditugu. Francesca Ferlaino, Vallet-Regí eta Lehnen eskutik. Eta ondoren, bertso saio berezi bat.
Halaxe da, Arzaldeko 8 aurrea, Bertso Passion saioa entzun ahal izango dugu. Amets Arzallus, Andoni Egaña, Maialen Lujanbio eta Nerea Ibarzabalen eskutik. Zientzia eta bersolaritza nahazten dituen formula hau dastatzera, gonbidatu nahi zaituztegu. Beraz, hitzaldi nagusiak bukatzean, ez mugitu zuen aulkietatik.
Bertso saio osoa euskaraz izango da, baina gogorarazi nahi dizuegu gaurko hitzaldiak ingelesez eta gaztelaniaz izango direla, beraz, konektatu itzazue itzulpen automatikoko gailuak behar duzuen kanalean.
Les recordamos que las conferencias de hoy serán en castellano y en inglés, así que si necesitan traducción simultánea, no olviden conectar el canal correspondiente en los dispositivos que les habrán dado a la entrada del teatro.
Y sin más dilación, les presentamos ya a la primera de las conferenciantes de esta tarde. Se trata de Francesca Ferlaino, descubridora de un nuevo estado de la materia, sólido y líquido a la vez.
Así es, Francesca Ferlaino es especialista en física cuántica y lidera un equipo de investigación en la Universidad de Innsbruck, en Austria, que recientemente llegó a un hito en la ciencia, el descubrimiento de un nuevo estado de la materia, con propiedades sólidas y líquidas a la vez. Este fluido tiene la estructura de un cristal sólido y robusto y al mismo tiempo las partículas en su interior fluyen como un líquido al estar deslocalizadas.
Azken urteotan, Ferlainok izen handiko sari eta intzatespen ugari jaso ditu. Besteak beste, Schrödinger saria, Feltrinelli saria, Alexander von Humboldt katedra, Innsbruck hiriko zientzia saria eta beste hainbat. Ez da erraza, kuantikari buruzko gaiak ondo azaltzea eta ulertzea, baina ziur gaude Francesca Ferlainok jakingo duela jakintzarekiko duen grina gurekin partekatzen, ezta? Beraz, entzun dezagun, adi-adi bere hitzaldia. Zero absolutuko temperaturara hurbiltzen diren atomoak, etorkizuneko teknologia kuantikoen hardwarea.
Francesca, engitorri, txalo ero bat, mesedez.
So it's really a fantastic honor to be here. And I would like, since I'm the first one of this afternoon, I would like really to take a moment to thank Pedro, Pedro Miguel Echenique, for having really the vision of creating this moment of passion of knowledge. And I would like also to take the time to thank Ricardo Diaz-Muñoz and all the team of Passion for Knowledge and the team of the Nostra International Physics Center to make this vision being such a beautiful reality today for us. And of course, for us as a scientist, it's already very clear that all this needs support from the institution, and so also from our side, I would say thank you to everybody. And now, so, Arantxaldeon denoi eta ongi etorri zientziaren maitale guztiei. Bienvenidos a todos. When I was invited to come here, I thought about what should I speak, and I decided to bring you to a trip. So a journey with me in a fantastic new world, which is the world of quantum physics. And so we will go together on some main thought that were, let's say, fixing the path of the development of quantum physics. And just at the end, I will tell you a little bit of what is our work. So when we start a journey, it's very important what is the feeling that we have inside of us. And what better feeling I can convey by using the word of Erwin Schrödinger, that was one of the founding fathers of the quantum mechanics. And he was saying something, I think, very deep and very important, which is the task, so the task of us, of scientists, is not to see what have never been seen before. That's not the task. But actually the task is to think what have never been thought before, thinking about what it's everyday life around us. And so this is the attitude, think different, think out of the box. This was the attitude of founding fathers of quantum mechanics. Indeed, although our reality is very beautiful, like you have here in San Sebastian, in reality, this complex reality is made of very simple objects, which are atom, molecule, and a photon. The photon are really small particles of light. Now, you might think that our reality is made of these elementary constituents, and they would kind of just be many of them, and that's it. But actually, that's not the case. So one is made of the others, but these two categories, the very small and our day reality, is extremely different in the sense that they follow different rules. Indeed, the world around us follows the rules of classical physics, while atoms, molecule, and photon are following the rules of quantum mechanics. This word quantum physics and quantum mechanics was introduced about 100 years ago by a number of scientists in a German school of Göttingen. And actually it was meant to give the sense that they would study the mechanics, the law governing the behavior of something which is very tiny and typically also very cold. Let's say temperature is not, a desired effect in quantum mechanics. And this was 100 years ago, and many, many things happened. And so many things happened that since a couple of years, we are speaking about a second quantum revolution. And I will try to explain you in our journey together why we speak about quantum revolution, what is the point? And actually, a few years ago, scientists around the world write down like a white paper showing the new opportunity of quantum physics, because some maturity in the understanding was also showing new doors to be open and new opportunity. Just to give you a sense, a few years after this quantum manifesto, this white paper, so the European Union picked up the challenge and decided that quantum physics and the related quantum technology are one of these disruptive new technology, which should be supported by a flagship technological program. And since then, many things happen around the world, and we have a number of development, and the word quantum became extremely popular and very much searched on Google. And actually, you see that also the support of, let's say, financial support to this domain of knowledge and science grow enormously. So by now, it's about worldwide about $22 billion, which are now invested in different way and in different countries about quantum science and technology. And of course, when such a big pressure is on the desk, there is also geopolitical dynamics. And indeed, there's an example in which you see the number of patents that China was putting together in comparison with USA, and you see how much these slopes start to become exponential. There is an interest, but now we would like to know actually why this is the case. And to do this, to answer the question why the physics of today became the technology of tomorrow, we need to do a step back. And I would actually do a very big step back. And I would go back to the 1920th century. And so why I want to go so far? Because that was the point in which the idea came that wave, let's say, can transport information. So the idea that actually waves are extremely important. So the light that it's propagating, it's a wave. They transport electric field, magnetic field, and in the properties of the wave, how fast they oscillate and how strong they are, one can encode information. And this idea of transmitted information was extremely, let's say, successful and powerful. And there was even this crazy idea at that time, okay, maybe we can send information very far away. The world immediately started to become smaller just because it was possible to connect. And how this became true? Well, many scientists have contributed. Now I put one which is Italian, so and that's my favorite example, which is Guglielmo Marconi, considered to be the father of the telegraph. And actually just at the beginning, the first year of the 19th, it was the first transatlantic transmission via this telegraph. A few years after, together with Carl Ferdinand Braun, he kind of won the Nobel Prize in Physics. But already, the telegraph sending, message over big distance. Okay, which message? What is the language, an easy language? That you can use in sending information. Well, this easy language, we know, each of us have heard, that's the Morse code. Why I put this example so far away, which has nothing to do with quantum physics? Well, because the Morse code somehow is something which, let's say, convert the alphabet, A, B, C, D, and so on, in a sequence of just two symbols. One is short, and the other is long. Short, like A, is short, long. B is long, short, short. So there is this idea that by having two values, so by having something binary, just two values, one can encode information. And this is actually the precursor of the same idea that it's used to have the bit in our computer. So in our computer, speak a language, a logic language of 0, 1, 0, 1, 0, 1, this binary logic. There are two values. You can call it 0, 1. You can call it down, up. Or you can call it low, high. But it's always two values. A very complex information you can encode in a string of 0 and 1. Maybe a very, very long one. And now that's the logic. That's our classical logic, how, let's say, computer science works today, or until today, and that's not enough. So the logic is a language. So now there is the language of 0, 1. This is working, is understood, but now we need an object which is able to speak this language, 0, 1. And in computers and microchip, this object that speaks 0, 1 is called transistor. And actually, the first use of this type of computer or big calculator, you might know from the movie of the Turing machine, and actually was a huge machine. Here is just one photo that was used to actually crack, let's say, a crypto system that was used during the Second World War by the German Reich. And here, basically, all these objects were precursor of the transistor. And inside the Turing machine, what you had, it's, let's say, this vacuum tube here. Pretty big. It's kind of a little coin size, which were able to give two values, and so to calculate based on this logic. Then the technology developed enormously in the 50s, and you had the first transistor, much smaller. And after the development of transistor, there was another huge boost in technology that was the use of integrated circuit, very small piece which contain many, many transistors. How many transistors do you have in the microchip of your computer? How many transistors are today in your computer? How many, so now you buy more and more powerful computer. How many of these objects that can speak 010101 do you have? Well, funny enough, there is an empirical law, which is amazingly good to be empirical, which is called the Moore law. And so it shows in this graph that since the 70s to roughly today, every 2 years, the number of transistors, the small object, in your microchip, in a computer, is doubling. And today, let's say the most up-to-date, let's say, processor that you have has about, you see, very big number, 50 billion of transistors are in this integrated circuit. Okay, but then something doesn't, you know, somehow we have more and more of these transistors, the computers are becoming smaller and smaller. That sounds kind of strange. So we can ask, what is the ultimate limit? And then what does it mean, more transistors, smaller computer? Where are we now? What is the limit? And now I show you two figures of merit for the limit. Oops. And one is about the size. How big is now a transistor? At the beginning, at the vacuum tube that I show you, were like a coin. And now we are going to size which kind of go below the size of a bacteria. And the ultimate size of one of these little transistors is kind of in the direction of a single atom. You can ask, okay, now how much current do I need to control one of these objects, because I don't want to spend and have gigantic bill at home because I'm doing something on my computer? Well, also here, technology advanced quite well, and you enter in a regime that you almost need very few, and at the limit, one electron to control. Size of one atom, one electron, the physics of the very small things. We are entering in the quantum world. We are entering to the necessity of asking ourselves, what is the law governing this very tiny object? And this is to say that from the technological point of view, so the watershed between classical world and quantum world is getting narrower. Just because the classical world is hitting now the bridge of quantum world. But that's not the only story, okay? That's just one part of the story. And now I will tell you the other part that actually interests me even more. And I will tell you, what does it mean, quantum? Because we speak about quantum a lot, but what it is? Maybe the first very important thing is related to the idea of energy, no? So our perception of energy is the perception of, for example, heating up something. You increase the temperature of something, the energy is rising, eventually the water is boiling, and eventually all the water is evaporating. We are giving energy. In our idea of energy, I can continuously give energy. But in the quantum world, the energy, you can just give it by one specific amount. You can, so let's say, either you give exactly this energy, or nothing happens to the system. What does it mean? If we want to heat up something in our microwave, and the microwave is quantum, and our food is quantum, it means that if you put 1 minute, then maybe you give 2 less energy, and nothing heat up in your microwave. But if you give 1 minute plus 1 second, boom, it's heating up. Pa, is a step. The idea is a step. Quantization adds a specific amount that make you increasing energy. Now, more technically, this is shown here. This black line corresponds to energy level. Let's say that the lowest one is 0, then you have a certain amount and a certain amount. This difference between these two values, this amount, is the one that you need to give if you want to excite something. If you give less, nothing happens. And so if you see this on a more geometrical point of view, the continuous classical feeling of energy, heating, and so on, it's kind of continuous. And when it's quantized, you need to give this step. That's very important, because now quantum objects are more protected. If I have something in one state and it's perturbed by some energy, nothing happens. It just needs really a lot of energy to be excited up. That's important. Another thing that is important is that you have lasers, and we already heard beautiful talk about lasers. And if you now shine a laser into one atom, the atom can absorb this energy and make a jump up. So the laser light is a very precise tool to control, let's say, the energy and then the state of an atom. I am in the ground state, down, very low energy, nothing happens to me, or I am in an excited state. And now you see, now just let's focus into these two levels, A1 and A2. Well, let's remember what we said about the Morse code, what we said about 0, 1. I mean, you can think that these two levels are actually really a very good transistor, because you have these two levels, 0 and 1. But actually there is even more, because atoms are special objects, and quantum mechanics teach us this. Because what is really the additional power is that you don't only, let's say, the energy level of an atom, it doesn't have to decide between 0 and 1. The incredible things is the system can be a little bit here and a little bit here. It can be in both states simultaneously. This is the first extremely difficult and counterintuitive law of quantum mechanics that we call actually superposition principle. And this already tells you that something is completely new in the logic that you have in quantum physics, and tells you that an object can be in, a state, can have both color, can have a certain part in the state 0, so the lowest one, and a certain part in the state 1. And this is why, to explain the superposition principle, many persons use the example of this so-called Schrödinger cat. So since the atom can be in both states, it's like saying that a cat closed in a box can be dead and alive in the same time. This can be, let's say, surprisingly, but that's a journey that we are doing together, where we are accepting that things are not completely deterministic. Okay? What does it mean in another term? Well, if you are a human classical world like us, you have two doors, you have to go on the other side, you have to decide either you go to the right or you go to the left. It's deterministic. You are determining what is your future, either here or there. In the quantum world, you don't need to have such a deterministic decision. Actually, in the quantum world, because particles have kind of wave and propagate, they can kind of pass simultaneously on both doors. They don't have to decide. We call this probability. There is a probability to pass on the right, the probability to pass to the left. But until you don't measure it, they are in kind of this superposition state of passing through both doors. And so now when you measure, I mean, you have a state and now you measure, then you have a probability to be in one state, but there is a kind of a weight to this probability, or you have the probability to be in the other state. But then you imagine immediately that the value, it's not only 0, 1, it's 0 multiplied by a probability, 1 multiplied to a probability. Saying again in another word, and hoping that one of these way will ring a bell of this very strange word. And for this strange word, I mean, there was a Nobel Prize in 2022 really proving some of the foundation like entanglement of quantum physics. To simplify, while the classical bit can take only 2 values, the quantum bit can take every value between 0 and 1, can take also 0.1. So you can imagine that it's much more efficient to put information in an object that can take any value. And so you need not so long string to encode complex message. And indeed, if you think about all possible combinations you could create only with 64 of these, actually this would be equal, you would need 10 to the 20, 10 to the 10, that means this big number of classical bits. So it's really fantastic, it's very powerful. And we call this quantum supremacy. But attention, there is an attention here very important. Although we might believe that the logic, it's really the quantum logic, and everything works very well, we need still to answer scientists need still to answer what is the proper quantum transistor. We have a language, but we need to find the proper object that is speaking this language. And this is really where there is today the technological race. I will not say much more on this. There will be another talk, I think, tomorrow about that. But I want now to point you out that the possibility of encoding information with this quantum bit is just one of the power of atoms. There is much more. Let me give you an example about this. We are still speaking only about one atom. And so I told you that the energy is quantized. I told you that you can use it for, efficiently encode information. But actually, you can also make, particle oscillating. And now this oscillation is reminding you a pendulum. Pendulum should remember you about a clock. And indeed, the most precise clock existing, the one on which the GPS is based, and you have the recognition of your location in every single mobile phone, this very precise clock is a quantum clock, which we call atomic clock. You use quantum technology every day of your life, maybe without even knowing. And another example is not all the story, because now I always consider that the level, this distance, this amount is fixed. But actually, you can change this amount. And the distance between two energy levels is extremely sensitive to magnetic field around you. So sensitive to be the best sensor possible that one can create somehow. And if you have a magnetic field, you would measure a difference in energy. To give you an example, based on this idea of two levels in quantum system, you can even think, you maybe know that the neuron in a brain is creating a very tiny, small magnetic field. And this quantum sensor of two quantum levels can be so sensitive to measure this field created and anomalies of this field. Or as I give you always an example, I kind of always tell that in my experiment, in my lab, if I look at the atom, because I have a very cold atomic system, I can tell you where is the elevator of the building. I can tell you, look, this energy difference tells me is in the 4th floor of the elevator. It's not very useful, of course, in the experiment, but actually tells you how sensitive can be one atom. It's a sensor as well. And all this is the power that you have in a single atom. And now imagine you have two. Wow, if one was so fantastic, two will be even greater. And imagine to have more than two, many more, that you have many. What will happen in this case? What can we understand about life around us when we make the transition between one atom and a many body, so many atom quantum system? Now we have to really ask, what is the phases? How do they organize? How do they share information between them? How efficiently you can, correlate one atom here and one atom there? There is a completely new journey that we have to start. And, but before this, we have a problem. And the problem is temperature. I mean, temperature means movement that you cannot really control of this atom. Temperature, we don't like. Quantum physics don't like very much temperature. So 20 years of research, fantastic research, was about learning how to cool down a gas, so you have several atoms in gas phase, and to remove thermal energy, to decrease energy. And this was really a very also genial idea, because what physicists find out that by shining light, a laser with the proper color, we can stop atoms. A laser which have no mass can stop, can decrease the temperature, can decrease the motion of something which actually has a mass. That's crazy. And let's say that we remove temperature. Now we will say, okay, you have removed a temperature, now everything is boring. Somehow things are not moving, it's everything frozen. No, now something else happens. You decrease temperature, and what happens is that every single atom loses the identity as an atom. It loses the identity, it's really like this, and it became a wave. When you decrease energy, you make this transition from the classical world to the quantum world, and every single atom starts to be delocalized. So it starts to be, has a probability again, to be in several places. So as a wave-type behavior. And let's say smaller is the temperature, longer is this wave. And now if you think about wave, and you have many of them, this wave can interfere. And when this interference become, let's say, positive, that all together, this wave work together and put themselves together, what you have is another transition of a giant wave, which is called Bose-Einstein condensate. Is a single macroscopic wave made of matters with about millions of atoms inside. They lose their identity. They are just part of this gigantic wave. And this was a big achievement in our field, but let me tell you, the way to cool down was a very challenging one. How cold should our atom be? And actually, to give a sense of what is cold, because if I tell you, I need to cool down the atom to nanokelvin, to you would mean probably nothing. What is nanokelvin? Also to me, this nano, okay, it's very low, but I want to give you a sense. And then to do this, I put a thermometer here. This is my scale that go to really very, 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 very low temperature, almost absolute zero, to very, very high temperature. Imagine that on this scale of thermometer, the hottest place in the world and the coldest place in the world are just 2.1 on top of the other. The scale is so long that the hottest and the coldest things that we can experience as human beings, they're almost the same point. And now, where is the surface of the sun? Well, It's nearby. And what is the coldest place in the background cosmic radiation? Well, it's also close by. And where we are going with our ultra-cold atom is here. Should be really extremely cold, at a point that we can even not measure anymore temperature. And to show you a bit how it looked like, in the experiment, we create a machine, we build this machine, we manufacture, we have a beam of atom moving very fast, and actually you might notice that while they move, they are in this blue light. They are absorbing this light and they're getting slowed down by the light. And eventually there are other light with other color that is kind of starting to collect all the atom in the center. That's gas. And this gas is kind of losing energy continuously. This phase is called magneto-optical trap. So it's still absorbing and emitting photon. You see that they move. And then, at a certain point, you are switching off all the light. Now let's see if it's coming. And you will do the last step of cooling. And the first Bose-Einstein condensate was in '95, was June '95, with this creation in which you see that suddenly all the atoms pick up and become one unique object. And for this, actually, there was the Nobel Prize in Physics 2001 given to Eric Cornell, Wolfgang Ketterlet, and Karl Weyman. And this opened a lot of possibility because now you have quantum physics, but at the level not of one atom, which is difficult to master, but really at the macroscopic level. We have 1 million of atoms all behaving as one entity, one wave, one macroscopic quantum object. And what we are kind of doing in our experiment, it's building up an object like this one that's really photo in our lab. There is a lot of mirror and a lot of light, and all this is manufactured at home. You cannot call a company and buy something like this. And what we like is to use a specific atomic species, one atom of the periodic table, and we pick it up for the first time, an atomic species which is extremely magnetic, which has a very strong magnetic field, and you know that magnetic interaction, you know, if you have two magnets, let's say you feel the force even before they touch, and so you see that the atom, even if they are away, they kind of get connected by this long-range interaction. And so the atom of choice for us were erbium and dysprosium. And we all like magnetic interaction. Stuff very interesting are happening, even playing with magnet in our day life. But now we don't have real classical object. Every atom is a quantum magnet. And because of these properties, you can see here that in general, magnetic interaction make a natural tendency of peeling up or creating a structure. And so that's what was the key to observe a new phase of matter. And indeed, what we know in our classical feeling is that solid exists, liquid exists, and gas exists. But actually, quantum mechanically, much more than these three categories is allowed. And actually, you can have even a state which it's in a gas phase and have both solid and liquid properties. And this is a state predicted in '57 called supersolid state, which is very difficult to, to depict because it's really a state of matter where you have the crystal rigidity, so the atoms are crystalline rigid, like in a solid, but at the same time they can flow like in a superfluid. These two things together is really hard also for me to imagine, and the best imagination I got is using a Greek god called Janus, because Janus is a god which has two faces, one looking at the future and one looking at the past. The future cannot exist without the past cannot exist without the future. And our God has a crystalline nature and a superfluid nature, but you cannot cut in two. And actually was very much debated whether a solid can be superfluid at the same time. And there have been theorists in the 50s, as you see here, that said, okay, these two properties cannot be combined. It's a little bit like the Schrödinger cat, dead and alive. Here we have a many-body state, crystal and fluid at the same time. So there was a physicist, very prominent, saying that these two orders are competing, cannot exist together. And there were others saying, yes, that's possible. Quantum mechanics allows it. And actually, both these four gentlemen had a Nobel Prize, so it's very high-level discussion. It's a highly non-trivial question, and there was a lot of experimental effort. And so recently, a few years ago, it was actually possible to observe the supersolid state using this ultra-cold atom. Thanks to their magnetic interaction, you see that a gas, it's really a gas, it's self-organizing, creating pattern like a crystal, like wave of density, but at the same time, each particle is indistinguishable and can flow everywhere. You cannot say which one is localized and which one is delocalized, like in a fluid. And then you can also have a very interesting pattern. So you have to figure out a gas that's self-organized, and every particle can flow without any friction. And with this, I would like now to conclude, and to close our journey, I conclude with another sentence, not from a quantum physicist, but from Nikola Tesla. And they say, and I think that's important to keep in mind, that the scientific person does not aim at an immediate result. We don't aim at an immediate result. But his or her duty is to lay the foundation for those who are to come and point the way. And this, I think, was the spirit of the founding father of quantum mechanics, and seeing how much have been developed since then. And let me actually end by saying thanks to my fantastic team in Innsbruck. We are having really a great fun, and I hope that the young generation will all become physicists and join this journey in their education. Thanks a lot for your attention. Thanks.
Really, listening and speaking in Basque with an Italian accent is really priceless. Eskerrik asko, Ferlaino irakaslea.
Hurrengo hizlaria ondo ezagutzen dugu Passion for Knowledge-en, izan ere, ez da zientzia jaialdi honetara etortzeko gonbidapena onartzen duen lehen aldia. Vallet-Regí da bera, eta hemen lagun artean hezurren birsortzailea deitzen diogu.
Bai, material zeramiko mesoporotsuen aplikazio biomediko potentzialak aurkitu zituen berak, baita farmakoak kontrolpean askatzeko sistemak ere. Arlo horretan egindako ekarpen aitzindariei esker, oinarrizko ikerketaren Jaime Lehna erregearen saria jaso zuen 2018an.
El grupo de investigación que dirige en la Universidad Complutense de Madrid está desarrollando diferentes estrategias para curar enfermedades relacionadas con los huesos, como el cáncer, la osteoporosis o las infecciones en implantes. Además, es la científica española más citada en el área de ciencia de materiales en las 2 últimas décadas.
Su conferencia se titula Biomaterials, ¿qué son y por qué los necesitamos? Profesora Vallet-Regí, un fuerte aplauso.
Bueno, buenas tardes a todos. Lo primero quiero dar las gracias a Pedro por esta magnífica, por ser el motor de todo esto que es fantástico. Por supuesto, Ricardo, a todo el de IPC, a todo el personal de Passion for Knowledge, que están trabajando para que todo funcione y para que estemos todos muy cómodos. Y a todos ustedes por asistir. Bueno, yo voy a tratar de contarles un poquito hoy qué son los biomateriales. Biomateriales son materiales, pero materiales que los vamos a utilizar para fabricar implantes. Y en estos momentos, si se fijan ustedes en esa diapositiva, podemos cambiar todo. Menos el cerebro lo podemos cambiar todo. Así que, claro, esto da para mucho. Y para todos nos va a hacer falta. Vamos a ver ahí un poquito qué son y por qué los necesitamos. Pues los necesitamos porque vivimos mucho. Fijaros que en la Roma imperial, la Edad Media, la esperanza de vida eran 22 años. A principios del siglo XX eran 40 y al final 80. Y ahora, aunque el COVID nos quitó un poquito, pero esto ha vuelto a remontar y vamos hacia los 90 de esperanza de vida. Claro, viviendo tanto, ¿qué es lo que le pasa a nuestros coches también? Cuando ya van teniendo años, pues hay que pasar a la ITV. Y en la ITV, ¿qué nos hacen? Pues nos cambian piezas de lo que haya hecho y nos lo vuelven a dejar nuevo o casi nuevo. Bueno, pues eso es lo que quiere o lo que pretenden los biomateriales. Todos los que se han tenido que poner ya algún implante o saben que se lo van a tener que poner en un futuro próximo, ellos o algún familiar, pues inmediatamente surgen tres preguntas. Pero bueno, ¿esto qué calidad de vida me va a proporcionar? ¿Esto me va a funcionar? ¿Va a ser mejor? ¿Vale la pena todo este lío? Luego, ¿cuál es el precio? Claro. ¿Y cuánto va a durar una prótesis implantada? Voy a intentar contar todo esto. Y para eso, pues me gustaría empezar con esta imagen. ¿Qué le pasaba al pirata Patapalo o al capitán Garfio? Pues les ponían algo que era, sustituir, no reparaban en absoluto, sustituían. Pero de ahí, a unos pocos años después, pues se podían ganar olimpiadas con cosas de estas. O sea que la tecnología ayuda a mejorar, pero todavía esto se queda muy viejo. ¿Qué es lo que ahora queremos? Pues realmente, como en la primera imagen que yo he puesto, que se puede sustituir prácticamente todo el cuerpo, ya digo, menos el cerebro, y solo las piezas, si vamos sumando lo que cuestan las piezas sin contar la intervención del médico, la hospitalización, todos los gastos que pueda conllevar, son unos 200.000 euros. O sea, por 200.000 euros tenemos un hombre nuevo, prácticamente, o mujer nueva. Pero claro, tampoco nos gusta ser el capitán Garfio o el pirata Patopalo. Y entonces lo primero que se hizo, el siguiente paso que se hizo, fue que tuvieran, las funciones. No solo poder enganchar, sino poder coger si era necesario. Pero ya el siguiente paso era que además tuvieran el aspecto del miembro que faltaba, de la mano. Todo eso ya se puede hacer. Todo eso ya lo podemos hacer. Y me parece que me he saltado. Vamos a ver otra pregunta que nos podemos hacer. ¿Cuántas se colocan? Una estimación de las que se colocan en el mundo. ¿Cuál va a ser su duración? O sea, si me ponen una prótesis, ¿esa me va a durar mientras yo viva o me la van a tener que cambiar enseguida? ¿O cuántos años puedo estimar? Y, por supuesto, clases de biomateriales para construir esas prótesis. Pues vamos ahí. En esta imagen lo vamos a ver casi todo. Lo primero, en este momento, en el mundo, se estima que 50 millones de personas tienen algún tipo de implante y muchos de ellos más de un implante. O sea que son muchos los implantes que se ponen. Primera respuesta. Segundo, ¿cuánto cuestan? Ahí tienen algunos de los precios. Cuando pone TI, todo incluido, como los viajes, y cuando no lo pone es el precio de lo que cuesta solo esa prótesis, ¿vale? O sea que ahí lo tienen. Hay para todos los gustos. Pero aquí lo que lo que tienen ahí, a ver si esto aquí. Ahí. Aquí, vamos a ver. Esta es una prótesis de cadera. Les he puesto eso porque, ¿saben que la primera prótesis de cadera se puso en Oxford en los años 50? Y que a España tardó muchísimo en llegar. La gente, cuando se rompía la cadera, pues esperaba ver cuánto aguantaba hasta morirse, que solía ser unos 15 días más o menos. Fíjense lo que ha corrido esto. Si ahora tenemos alrededor un montón de gente que tiene prótesis de cadera de todas las edades, porque también los accidentes obligan a los jóvenes muchas veces a cambiarles las prótesis. Bueno, pues aquí la tienen. Y decíamos, ¿qué materiales? Pues los materiales que se utilizan para las prótesis suelen ser materiales funcionales, o sea, metales, cerámicas y polímeros, o materiales híbridos de todos ellos. Y fíjense que aquí, en una prótesis de cadera, que es la que he elegido, tenemos los 3 materiales. En el vástago, que nos hace falta fuerza, se usan normalmente los metales, que pueden estar recubiertos por cerámicas para que tenga mejor adherencia. El cotilo siempre es de polímero, para que pueda fluir bien, porque claro, lo que queremos es andar con esa prótesis. Y la cabeza pues puede ser de cualquiera de los tres metales. O sea que yo con eso creo que ya he respondido a algunas de las preguntas que se pueden hacer. Ahora la otra pregunta es, ¿cuánto nos cuesta a los que trabajamos en este tipo de implantes, desde que uno tiene la idea hasta que le llega al paciente, cuánto tiempo pasa? Pues pasan unos 10 años, más o menos, porque ahí hay que pasar, bueno, pues lo primero tener la idea, fabricarlo, buscar los materiales apropiados y fabricarlo, y después, bueno, patentarlo, todas las fases clínicas, y hasta que le llega al paciente aproximadamente 10 años, lo cual es mucho tiempo, pero es absolutamente imprescindible. Ese tiempo es difícil rebajarlo. A mí me gustaría que esto lo miráramos todos con atención. He dicho al principio que a principios del siglo XX la edad media eran aproximadamente unos 40 años. Entonces, claro, si eran unos 40 años y vemos la robustez, la fragilidad, la discapacidad, y cuando llegaba la muerte, que eran los 40 años, pues nuestros antecesores, bueno, vivían poco, pero no tenían el problema que tenemos ahora de vivir con discapacidad. Ellos se morían a los 40, pero raro era el que tenía discapacidad a esa edad. Y, por supuesto, la osteoporosis no se conocía, no sabía ni lo que era esa enfermedad, porque llegaba más tarde. Por tanto, ahí nosotros el vivir más y vivir mejor sin discapacidad es algo que tenemos que conseguir con los biomateriales, porque vivir más, pero para estar discapacitado, para esos señores no vale la pena. Entonces, ahí, si ahora alargamos esto hasta los 90 años, que es lo que hemos dicho que estamos en la línea de conseguir, pues ¿qué es lo que pasa? Pues que tenemos ahí un problema, porque claro, el que ha tenido un envejecimiento exitoso va bien, pero el que ha tenido un envejecimiento acelerado, y mucha gente sabemos que la tiene, pues tiene un largo camino muy molesto en su vejez. También eso tenemos de alguna manera que solucionarlo. Aquí tenemos un hueso sano de una chica jovencita, y aquí tenemos un hueso osteoporótico de una persona anciana, en donde, claro, ¿qué diferencia hay? Pues es mucho más, las paredes son mucho más delgadas y tienen aquí unos poros mucho más grandes, por tanto, huesos muy frágiles. Se llamó en su día la enfermedad de los huesos de cristal, por eso, porque bueno, cada vez que había una caída podía romperse. Cuando fabricamos cualquier tipo de implante, lo primero, y elegimos los materiales, lo primero que tenemos que pensar es la composición. Entonces, bueno, este es sentido común. En química sabemos bien que los equilibrios son los que mandan y sabemos la importancia que tienen los equilibrios químicos en el cuerpo humano. Tenemos una serie de elementos que lo componen y entonces lo que no conviene en absoluto es romper mucho esos equilibrios. Es verdad que a veces vamos a tener que poner elementos que no son de los, vamos a llamar entre comillas, buenos, pero con dosis muy pequeñas son perfectamente aceptables, mientras que de los beneficiosos, en determinadas dosis excesivas, pueden ser absolutamente peligrosos. O sea que ahí tenemos que jugar en la composición con lo que vamos a tener que meter en el cuerpo y que eso no produzca más daño de lo que va a arreglar. Luego, otra cosa que hay que tener en cuenta, además de la composición, es la superficie de ese implante. ¿Por qué? Porque lo primero que va a llegar a la superficie del implante, lo primero, van a ser las moléculas de agua de nuestro cuerpo. La mayor parte del cuerpo, lo acabamos de ver en el anterior, más del 50% de la masa corporal es agua. Lo primero que va a llegar es el agua. Si esa superficie rechaza el agua, es hidrófoba, ya tenemos problema. Y si le gusta, aquello va bien. O sea, que sea hidrófoba o hidrófila va a ser importante. ¿Por qué? Porque lo siguiente que va a llegar van a ser las proteínas. Las proteínas solo van a estar cómodas cuando esa superficie haya sido hidrófila y haya aceptado el agua, y a continuación llegan las células, y las células solo van a estar cómodas si las proteínas donde van a adherirse lo están. Y naturalmente cualquier implante que pongamos tiene que tener necesariamente que aceptar a las células para que las células ahí puedan adherirse, crecer y proliferar. Si no, ese material no es válido como biomaterial. El biomaterial, ¿qué es? Es un material bio porque se utiliza para reconstruir el cuerpo humano y va a estar en contacto con los tejidos vivos. Por tanto, es algo que va a estar dentro de nuestro cuerpo. Esa superficie, además, claro, si esas células tienen que pasar por unas zonas, si es lisa o es un diente de sierra, no van a estar igual de cómodas. Luego, la rugosidad, la mojabilidad, la movilidad superficial, por supuesto la composición química, como acabo de decir, la carga eléctrica, la cristalinidad, todos esos factores hay que controlarlos en esos biomateriales. Y para eso, y teniendo además en cuenta que en estos momentos tenemos técnicas para llegar a poder identificar la materia a nivel de los nanómetros, pues evidentemente hay que caracterizarlo eso, porque si nos quedamos en solo lo que ve el ojo, es decir, en los milímetros, lo que nos hace el odontólogo cuando nos pone un implante, pues ahí solo está viendo el titanio y el hueso. Pero no es verdad, porque ahí si lo miramos con una longitud de onda que nos permita identificar las micras, vemos que entre el hueso y el titanio hay una serie de biofluidos de nuestro cuerpo. Pero si además lo hacemos ya a la escala del nanómetro, pues lo que vemos es que entre ese biofluido y el titanio está la capa de óxido de titanio, que es precisamente la responsable de impedir que se oxide ese implante, porque es el parapeto para que la oxidación, para que no le pase lo que al hierro. Aquí en la concha, esa barandilla tan bonita que hay y que siempre ya, aunque la estén pintando y manteniendo, siempre tiene el reflejo de esas manchas de hierro como consecuencia de la oxidación. Y si no se mantiene, eso se termina oxidando en su conjunto y queda como un polvo. Eso no le pasa a los implantes, porque esa capa de óxido que lo pasiva lo impide. Luego es importante la caracterización a todas las escalas. Y tenemos ahora, los fabricantes de implantes tienen la obligación de hacerlo así, porque si solo nos quedamos en la caracterización bruta, nos estamos perdiendo lo mejor de la película. Bien, aquí por ejemplo estos son de los implantes que hacemos en el laboratorio, de los andamios para recubrir hueso, y vemos cómo, bueno, pues si lo vemos en la escala del milímetro estamos viendo muy pocas cosas, pero si nos vamos a lo del nanómetro podemos ver que eso lo estamos fabricando con unos tamaños de poros del orden de 2-3 nanómetros que nos permite meter fármacos para además poder curar al tiempo de poner el implante que haga la función para la cual lo estamos eligiendo. Bueno, pues ya sabemos cómo tenemos que hacer los implantes, ya lo tenemos todo organizado, pero hay complicaciones. Cuando me ponen un implante, ¿voy a tener complicaciones? Pues, por ejemplo, si seguimos con el ejemplo de la prótesis de cadera, tenemos dos complicaciones fundamentales, que es el aflojamiento. Pues claro, hemos puesto la prótesis de cadera para poder andar. Y eso, ¿qué es lo que pasa? Que hay micromovimientos. Se desprenden partículas de desgaste, que ese es otro problema, que pueden circular por todo el cuerpo. Pero en ese desgaste, pues, y con esos micromovimientos, se afloja la prótesis. Y si afloja la prótesis, eso es un problema que puede, en muchos casos, obligar al recambio. O sea, que ese es uno de los problemas. Y el otro, que es el que quiero hablaros un poquito más, es el de la infección. Y la infección, cuando hay una infección de una prótesis, ¿a quién le echamos la culpa inmediatamente? A la prótesis, estaba infectada. Al médico, estaba un cochino que no sabía limpiar las manos. A cualquiera. Pues muchas veces, la mayoría de las veces, la culpa la tiene el propio paciente. Porque, por ejemplo, un paciente que tenga una infección en boca, que a lo mejor ni siquiera es consciente de ella, esa infección, esas bacterias son muy listas y se van ¿a dónde? A ese elemento que hemos puesto ahí nuevo y que es extraño, ¿no? Y entonces muchas veces la infección se debe al propio paciente. ¿Y qué es lo que pasa cuando un implante, que ya lo hemos colocado, por tanto hemos dicho que tiene que estar en contacto con los tejidos vivos dentro del organismo, qué es lo que le pasa? Pues que llegan las bacterias son muy listas, les encanta además ser gregarias, van todas juntas a esa zona y forman lo que se llama un microfilm. Es decir, están agrupadas y automáticamente con unos mucopolisacáridos se recubren de la misma manera que aquí cuando hay chirimiri nos ponemos el chubasquero. ¿Para qué? Para que no nos entre el agua. Ellas, ¿para qué se organizan ese biofilm? Para que no puedan entrar los antibióticos y las puedan molestar. Por tanto, cuando hay una infección, ¿qué es lo que pasa? Que se dan antibióticos y los antibióticos van por todo el cuerpo, pero no llegan a donde tiene que llegar porque las bacterias han organizado su biofilm que impide la entrada en las bacterias. Bueno, pues para eso también hay que buscar soluciones para los implantes y para eso tenemos muchas alternativas. Pero un inciso aquí, y es que en todo esto de los implantes hemos entrado el mundo de la nanotecnología. Hace unos años era ciencia ficción, ahora ya es una realidad. Y ahora podemos perfectamente pues, fabricar nanopartículas de unos 100 nanómetros. Para hacernos una idea, el espesor de nuestros pelos son 80.000 nanómetros, el espesor. Y lo vamos a fabricar de 100. Y lo vamos a fabricar, lo podemos hacer en el laboratorio con muchos poros de unos 2 nanómetros. Los antibióticos miden cada molécula 1 nanómetro. Y bueno, pues con esos antibióticos los podemos meter en esas nanopartículas, las podemos cerrar también químicamente con compuertas moleculares y que sean capaces de responder a determinados estímulos que lo hagamos. Y entonces ahí tenemos, pues podemos aplicar luz, ultrasonidos, calor, bueno, todos los estímulos que ven ahí, para que sea un sistema inteligente, on-off, como cuando encendemos y apagamos el interruptor de la luz, que permita abrir las compuertas y salen los fármacos, cerrar las compuertas y se quedan retenidos. Y de esa manera podemos utilizar esas nanopartículas dentro de muchos de estos implantes o en la superficie de estos implantes. Todo lo que les he contado lo voy a resumir, es lo de aquí. Si nos pasa ahora algo, y vamos al hospital porque nos tienen que poner algo, es lo que les he contado. Por favor, el vídeo.
Los biomateriales se fabrican con componentes naturales o artificiales, que necesariamente tienen que ser compatibles biológicamente con el cuerpo humano. Se utilizan para reparar o reemplazar un tejido natural dañado, como por ejemplo huesos, dientes, piel, y en un futuro próximo, tejidos de órganos como hígado, riñones, etc. El objetivo que se persigue al utilizar biomateriales es salvar y mejorar la calidad de vida, reducir el sufrimiento y retrasar los efectos del envejecimiento de la población. Desde soluciones muy primitivas hasta la regeneración de distintos tejidos, no han pasado ni 70 años. los grandes desarrollos en ciencia y tecnología han sido espectaculares. Esta disciplina se enmarca dentro del campo de la ingeniería biomédica y es multidisciplinar, donde tienen que trabajar muchos profesionales de forma conjunta. En huesos, actualmente se requieren más de 2 millones de injertos óseos al año y las soluciones disponibles incluyen el hueso autólogo o de donaciones. Los biomateriales son esenciales para regenerar hueso en situaciones poco favorables, como cuando hay defectos críticos o se produce una infección. Los autoinjertos son el patrón oro, ya que sus poros, de diferentes tamaños, las biomoléculas osteogénicas y las células madre hacen que sean osteoconductores, osteoinductores y osteogénicos. Sin embargo, los autoinjertos tienen limitaciones, como la cantidad de hueso disponible y el aumento del tiempo de cirugía, morbilidad y dolor. Una opción es utilizar la ingeniería de tejidos. En todos estos biomateriales implantables, la ciencia y tecnología está imponiendo nuevos diseños y combinaciones, nuevos recubrimientos, nuevas tecnologías de diseño y fabricación que revolucionarán a corto plazo el campo de los implantes. Materiales biomiméticos, biomateriales funcionales, nanotecnología, modelización por elementos finitos, manufactura aditiva, impresión 3D, ingeniería de tejidos, liberación de fármacos. Los nuevos biomateriales, además de regenerar tejido, deben proporcionar soporte mecánico durante la curación y evitar posibles procesos de infección originados por la cirugía. Los enfoques de ingeniería de tejidos buscan regenerar el hueso utilizando terapias de células troncales y pluripotenciales. La ingeniería de tejidos del hueso parte de soportes porosos biocompatibles, fabricados a menudo con biocerámicas bioactivas, fosfatos de calcio, vidrios bioactivos, osteoconductoras, que se decoran con moléculas osteoinductoras y en los que las células osteoinductoras puedan diferenciarse y proliferar. Pero todo esto tiene que llegar desde el laboratorio al paciente, por lo que es imprescindible realizar una investigación translacional.
Bueno, pues hasta aquí lo de si nos pasa algo, vamos al hospital, esto es lo que nos van a poner. Pero, ¿en qué se está investigando ahora en biomateriales? ¿Qué es lo que se pondrá a nuestros hijos? Pues va a ser muy distinto. Vamos a pasar de sustituir, que era lo del capitán Garfio, a reparar, que es lo que se hace ahora, a regenerar. ¿Y eso cómo se va a hacer? Con la ingeniería de tejidos, entre otras cosas, para lo cual se aíslan células del propio paciente, se hace que proliferen, se siembran en un andamio, como los que les he puesto antes, de los que hemos visto en distintos tamaños, y una vez que ya han proliferado y ya están óptimos, el cirujano los coloca en el cuerpo humano. Eso es la ingeniería de tejidos. Y ahí, fíjense otra vez, otra reflexión. Hemos dicho que el envejecimiento hace 100 años, a principios del siglo XX, pues la gente se moría a los 40, pero bueno, pues tampoco tenía una vejez de la que no queremos tener ninguno. Ahora, ¿qué es lo que pasa? Pues si se fijan en lo que tenemos ahora, el envejecimiento normal actual, y siendo optimista, el último cuarto de nuestra vida, pues la pasamos fastidiada, con muchos problemas. ¿Y qué es lo que queremos con la medicina regenerativa? Llegar a la misma situación del siglo XX, pero en el siglo XXI, en donde podamos vivir pues, los 90 años que hemos dicho, pero sin discapacidad y sin problemas de vista, problemas de oído, sin Alzheimer, sin Parkinson, etcétera, etcétera. Entonces, para eso, algunos de los objetivos de esa medicina regenerativa, que es en lo que se está trabajando ahora, pues está en la regeneración de la médula ósea, el nervio óptico, lo que les decía, poder ver, poder oír, todo lo que sea, quien tenga un infarto, que pueda tener una regeneración cardíaca perfecta, el Parkinson y el Alzheimer, pues intentar buscar soluciones, minimizar las secuelas de los trombos, la terapia celular para los diabéticos, que también las cantidades, como ven ahí, son enormes, nuevo tejido, cartílago, músculo, tendones, ligamentos, discos vertebrales, etcétera, etcétera. Bueno, pues para eso, en la historia de la regeneración, empieza con el Premio Nobel de Fisiología, con Shinya Yamanaka, que lo que él hace es, o lo que él pronostica que puede darnos buenos frutos, y ahora veremos si lo dan o no, es reprogramar las células. Arriba tenemos una célula madura y abajo una célula inmadura. Son con las células IPS, que es con las que él ha trabajado. Y entonces, fíjense, esto es nuestra vida. Empezamos con la generación, llegamos al punto máximo y llega ya la degeneración hasta que llegamos a la última etapa, que es vejez, enfermedad. Entonces ahí, en esa diferenciación, eso es un proceso natural. Es en la parte de arriba, desde que de los bebés hasta llegar a la edad adulta, hay una diferenciación como proceso natural del desarrollo. Y determinados vertebrados sabemos que tienen un proceso natural de regeneración por una desdiferenciación limitada. Los humanos no, pero ese es el trabajo de Yamanaka, intentar reprogramar para conseguir pasar a células desdiferenciadas que permitan esa rejuvenación. Y él lo ha hecho con una serie de líneas IPS. Él es japonés, trabaja en Japón o trabajaba en Japón y tiene pues, con 4 alotipos de pacientes japoneses. Pero eso, ¿qué es lo que le pasa? Que llega que sean compatibles al 40% de los japoneses. Pero ahí llega otra vez la tecnología y la tecnología da un avance fenomenal a esto, que es la edición del genoma. Y con la edición del genoma resulta que ese stock de células IPS con genoma editado, en vez de 4 ya puede ser 10 líneas, y eso abarca prácticamente a toda la población mundial y además, claro, el precio baja drásticamente, con lo cual es mucho más asequible. Y vamos a poner el vídeo de a dónde
La
vamos.
medicina regenerativa es la especialidad que se ocupa de regenerar tejidos y órganos, y ya se han logrado avances significativos en el tratamiento de enfermedades degenerativas, enfermedades autoinmunes y en estética. Junto a las terapias celular y genética y a la ingeniería de tejidos, se conseguirá la autocuración del organismo gracias a los avances tecnológicos y el trabajo de los científicos. Para realizar ingeniería de tejidos, lo primero es recolectar células del paciente, aislarlas, hacer que proliferen, a continuación, sembrarlas en un andamio y cuando hayan proliferado y diferenciado en condiciones óptimas, se implanta el andamio. La ingeniería de tejidos tiene 3 protagonistas principales: los andamios, las células y las señales biológicas. En el caso de huesos, puede hacerse una analogía con la construcción de una casa, donde los andamios serán las guías, las células, los albañiles y las señales biológicas, los permisos de obra que permiten la formación de nuevo hueso. La idea global en la ingeniería de tejidos es implantar un andamio con células y señales biológicas, que va a regenerar el hueso al mismo tiempo que el andamio va desapareciendo. Es muy importante diseñar bien los andamios, donde hay que controlar composición, porosidad y nanotopografía. La composición del andamio debe basarse en materiales biocompatibles con el cuerpo humano, que sean capaces de regenerar la matriz ósea y que además tengan la capacidad de disolverse a una velocidad apropiada. La porosidad tiene que ser adecuada para que las células puedan acceder y colonizar todo el andamio y permitir el aporte de nutrientes y de oxígeno a las células. Por último, la nanotopografía, es decir, el terreno en el que se encuentran las células, que tiene que ser confortable para que se sientan a gusto y colonicen el andamio. El grupo de María Vallet-Regí está trabajando en diferentes técnicas para fabricar estos andamios, entre los cuales destaca el prototipado rápido. Los andamios se fabrican con impresoras 3D capaces de controlar la porosidad con gran precisión. Esta técnica va encaminada al desarrollo de terapias personalizadas. Se empieza haciendo un TAC al paciente para poder reproducir el defecto óseo. se pasan los datos a un ordenador y finalmente se imprime en 3D. De esta forma, el andamio tendrá la misma morfología, tanto interna como externa, que el defecto del paciente. El trabajo fundamental del grupo de investigación de la profesora María Vallet, con respecto a la ingeniería de tejidos, se ha centrado en la síntesis de numerosas biocerámicas y con ellas han fabricado andamios, han puesto a punto recubrimientos cerámicos sobre andamios metálicos, han realizado estudios in vitro e in vivo de todos estos andamios, con el valor añadido de que dichos andamios puedan ser, además, liberadores de fármacos cuando sea necesario. Se han mejorado las propiedades de las biocerámicas de partida adicionando pequeñas cantidades de óxidos de elementos que les confieren capacidades osteogénicas, angiogénicas, antibacterianas, antiinflamatorias, hemostáticas o antitumorales. Además, estas biocerámicas son versátiles, ya que se pueden procesar como andamios, fibras, recubrimientos o nanopartículas, y se pueden mejorar aún más incorporando biomoléculas, fármacos y células madre.
Pues, con esto ya quiero terminar, pero quiero hacer una reflexión. Y es que he dicho que la primera prótesis de cadera se puso en los años 50 en Oxford, pero no igualmente de todos esos que les he puesto en la primera diapositiva, todas esas piezas, todas estas son de los años 80, 90 y también para adelante, ¿no? O sea que realmente ha corrido mucho. O sea, estamos acostumbrados a esas piezas de repuesto, a pasar por esa ITV y volver a estar sanos. Pero es que esto no hace mucho tiempo, ¿no? Nuestros padres, nuestros abuelos no pudieron tener esas piezas. Fíjense que las primeras definiciones de biomateriales fueron en 1986 y se vuelven a repasar y a actualizar en el 2018. ¿Qué pasa? Que con la tecnología, con las nuevas tecnologías, irrumpen un montón de nuevos materiales, de nuevos biomateriales. Hay nuevos que hay que meterlos, hay otros que se quedan obsoletos. Es que al principio los materiales se usaban materiales para otras aplicaciones, pero que si eran compatibles con el organismo se ponían. Ahora no, ahora se fabrican especialmente para el cuerpo humano. Así que, bueno, pues solo decirles que es un campo que tiene 70 años como mucho, lo cual no es mucho en el mundo de la historia y del mundo de los materiales. Y quiero terminar dando las gracias a las traductoras por el esfuerzo que han hecho. Espero haber vocalizado para que lo pudieran hacer bien. Muchísimas gracias y a todos ustedes por su atención. Muchas gracias.
Profesora Vallet-Regí, muchísimas gracias.
A continuación vamos a tener el privilegio de escuchar al padre de la química supramolecular, nada más y nada menos que a Jean-Marie Lehn.
Lehn recibió el Premio Nobel de Química en 1987 por su trabajo sobre la base química del reconocimiento molecular, es decir, cómo se reconocen y se ligan las moléculas de forma selectiva, algo fundamental en los procesos biológicos. Su trabajo le llevó a definir la química supramolecular o la química más allá de la molécula, centrada en las entidades complejas formadas por la asociación de dos o más especies químicas.
Urratsak materia konplexurantz, kimika, izena du gaur eskainiko digun hitzaldiak. Atzoia da Bilboko Euskalduna jauregian entzun ahal izan zuten haraino bertaratu zirenek. Bihar berriz doktore gaientzako prestakuntza bat eskainiko du Miramar jauregian eta ostiralean ikaslekin egingo den topaketa baten parte hartuko du.
Benetan emankorra Jean-Marie Lehnen bisita eman diezaiogun ongi etorria txalo zaparrada batekin.
Good evening. I don't see much, but I see you just so. This is a fantastic time again. It's not the first time I was at this meeting, at this congress, at this passion for knowledge. And I think we should thank the person who has started it, Pedro Echenique, and all the staff who did all the work for making it better and better and better every session. So, my talk has to do with what chemistry is doing in everything that we have heard about. The previous talk was very chemical. So what are the steps towards complex matter? Chemistry are main steps in that. And it started very early on in a Big Bang. At that stage, after the Big Bang, the universe inflated, became very big in a very, very short time. And then, progressively, the temperatures went down, particles formed, and at the age of physics developed no chemistry. The conditions were not correct for chemistry. Particles formed, they formed atoms. Atoms then got together to make molecules. And then chemistry started. So the age of chemistry is the age following that of physics. That the evolution continued and molecules became more and more complicated, larger, and they formed aggregates. They formed also compartments. And then a new property appeared, which we don't know yet exactly how it happened, but there's just another meeting going on the origin of what we call life. Life on Earth appeared about there. That's the age of biology. But luckily, life was not the final property. The final property of interest is the one which makes us be here, which is thinking, represented by this famous statue of Rodin, Auguste Rodin, the thinker, and that's steps towards complex matter. And one individual we might consider in that is this one. Are you complex matter, Pedro? Okay, so, yeah, you're a bit complex, I know. So, this is not a dark slide. It's dark, but it's not the reason, it's not a bad slide. We know nowadays, from many observations, that the universe is formed of 68% of dark energy, 27% of dark matter, more or less. That means 95% of darkness, very dark, but 5% of visible matter. And that's the matter that matters. That's our matter. We are just part of 5%. But this 5% can try to understand the 95 which are left there. So evolution came from divided matter, then condensed matter, then organized matter, then living matter, then thinking matter, and something else after that, maybe something beyond our own thinking. Very difficult to imagine what it can be, but we cannot exclude it. And this is the step towards complex, more and more complex forms of matter. Then we have a big question to ask, a very big, very fundamental question. How can matter become complex? From elementary particles to a thinking organism? And are they perhaps even higher forms, more complex forms of matter? To give an answer to that, mankind on our planet, this piece of dust in our universe, has created what we call science. If you just look at three pillars, or three parts of science, physics deals with the basic laws of the universe. Everything depends on these basic laws. Everything is dependent on how these basic laws operate. pardon. Biology deals with the rules of life. They are not laws, they are rules. The laws are already given. So what is chemistry doing? Chemistry is trying, and you have probably guessed what has happened, to build the bridge between the two. How do you go from very general laws to a specific expression of these laws like a human being on our planet? And of course, there are many other planets, and there are very probably many other living organisms on other planets. How does this happen? We can look at it from our point of view, from our piece of dust sitting in this enormous universe. And one may say that the answer to the question is, at least I give that answer, self-organization. That means that our universe is constructed in such a way that it will self-organize somewhere. Not everywhere, but somewhere. One can even go in terms of, let's say, philosophical outlook, one step further and say that it's a cosmic imperative, that our universe has a structure such that life will not be an accident, life will be an imperative, will be a consequence of the structure of our universe. Now, our universe is made of bricks, and these have been analyzed over the years, and one knows that there are a number of bricks making up this visible matter, this 5% of visible matter. Here you see the table. So you all here are part of this organism, thinking organism, which was able to put together the bricks which make up visible matter in our universe. There are no others. I'm very astonished by that, and also I'm not so happy about it because it looks like it's limited, but this is the table of the elements, and an element in here on our planet will be the same somewhere else, far, far, far away. So this is the Lego set with which visible matter is constructed in our universe. It's because of that that we know when a water molecule is present on another planet very far off, we can know that it is a water because it has the same properties, the water molecule. And that's the playground of chemistry. Chemistry is, chemists are like children. They like Lego, they put things together, they make constructions, and there's an enormous number, of course, an infinite number of constructions one can realize, and some are realized already. These are the ones we find in nature. Others await to be made by mankind or by others on other planets. So from the atom to the molecule, taking bricks, taking atoms, putting them together, making molecules, houses, molecular chemistry has started by linking these atoms together strongly by what chemists call covalent bonds, and this then led to this great variety of molecules which make our bodies. We have heard some in a previous lecture, many examples of materials. And of course, there's a very infinite variety of them. If you want to look at two milestones, I would just like to show you two milestones, how this has evolved. In 1828, man is considering that that's the time where more or less the art and science of making molecules from atoms has had the first step of importance, when Friedrich Wöhler in Germany made urea from another chemical compound called ammonium cyanate. Now, don't worry about the name, but ammonium cyanate is not contained in living organisms. Urea is contained in urine. At that time, people were thinking that in order to make in the laboratory anything which was present in a living system, you had to use a magical force called the vital force. Wöhler, by making from ammonium cyanate, which is not contained in organisms, urea, showed that this was totally wrong, that molecules are molecules, if they are in a living organism or if they are inorganic or not living, it's just the same. So life has nothing special. The building blocks of life are normal molecules. 150 years or so later, this very big molecule was made in the laboratory by putting together the right atoms in the right position, and stepwise, it took two groups collaborating across the Atlantic, Robert Burns Woodward in Cambridge, at Harvard in Cambridge, Massachusetts, and Albert Eschenmoser in Zurich, at ETH, Polytechnical School in Zurich. That's a much, much more complex molecule to urea. It took many, many years, many, many people to build it up progressively. I was one of them to work at that time. I worked with Woodward. And so this built up and was realized. It looked at that time like the Everest of the art and science of making complicated molecules. And vitamin B12 is present in our blood. Of course, since that, molecular chemistry has become more and more evolved. It has had new reactions, made new products, new drugs, new materials, and so on. And it will continue for many, many, many years. But we can have then a question to ask. We can say, what else? What is something else we should like to study beyond what molecules are? And here one can illustrate it in the following way. Here you see a blue ball, which is a cancer cell, and two purple entities, which are killer cells, which are part of our immune system. These killer cells have to find the cells which have become cancer cells and to destroy them. How do the killer cells know that the other one is a cancer cell? If they make a mistake, you have a big problem. Either you destroy a healthy cell, or you do not destroy a cancer cell. Both are not very good for you. Similarly, a virus can infect a cell by colliding with the cell and then finding the point of entry and then infecting. We know recently that this has happened not so long ago, where one had really to handle this new problem of this virus which was infecting most of us, and in the pandemic, which we came just out of it. So the question then is, what is going on? What makes killer cells know that the other one is a cancer cell? What happens here is obviously that these bodies are made of molecules, and they touch each other. And by touching molecules which characterize a cancer cell, and they are on the surface of the cell, there are some molecules which are sitting there, and the killer cells, they find them, and when they find them, they try to destroy them. So beyond molecular chemistry, therefore, beyond isolated molecules, single molecules, there is a field which deals with what assemblies of molecules do. And this we have called supramolecular chemistry, which is chemistry beyond the molecule, chemistry of assemblies, of societies, of populations of molecules. And this is then a field which is, of course, important in terms of what our new properties are appearing. Let me just very quickly give you an example. A single water molecule cannot boil and cannot freeze. A glass of water can boil and freeze and have a viscosity, an index of refraction, and so on. It's still water, but the difference is in a glass of water, molecules interact. And here come a lot of new properties. And so as complexity of the system increases, new properties appear along the way. So this is then trying to go beyond the single isolated molecule and seeing what happens when they get together by interactions. For physicists, that's all the same, of course, and they are right. But for chemists, it's just convenient to try to sort of have to separate molecular interactions, covalent interactions from the non-covalent ones. And several properties have been studied over the years. One of is molecular recognition. I come back to that. Also how molecules react with one another when they get together, and also how they can carry one another through a membrane, like a cell membrane or an artificial membrane. What is molecular recognition? Very simple to explain that. It had already been done many, many years ago. Molecular recognition first involves binding. If you have no binding, no interaction, then you ignore. They would ignore each other. So there must be some kind of energy, some kind of glue to put them together. But there is a very important property, which was probably the most important property which supramolecular chemistry made apparent. Of course, it was always there, but you have to realize it is there, and this is information. Molecular systems, when they come together, they have the molecules have information, and when they come together, they can process that information. So there is a sort of a double complementarity in very simple terms. The geometry fits together, and the interactions also fit together so that they attract or repel. And in fact, in 1894, there was already a very, very famous paper which sort of expressed that in a very nice and strong image. And if you just recall that image, if you remember this image, that's enough for the talk I give today. It is Emil Fischer, who in 1894 wrote a very famous paper when an enzyme, trying to explain how an enzyme acts on its substrate, the compound it has to transform. He said they have to fit together like Schloss und Schlüssel, like a lock and a key. And of course, if you have a lock and a key, if they fit together, you can open the door, you have a function following, and so on. So this was a very, very important paper which was published in 1894. Now, the emblematic example of that is the genome on our planet of living organisms. The genome is a way to store molecular information, and in fact, it is very, very simple, even trivial, I would say, when we hear about all these magnificent machines now when they are made for quantum physics, for quantum objects, for all these materials we heard about, which are much more complicated in terms of the molecular structure they have. Here, we have just 4 chemical letters. This means 4 small, simple chemical groups which have received names given by chemists: adenine, guanine, thymine, cytosine. They are sitting on a long string in a given sequence, and this sequence is characteristic of what this information is. So the difference between a tomato and an elephant is in that string. Just a sequence of 4 letters makes the difference. Now, how can this be read? It's not enough to store the information. You have to be able to process it, to read it. It is also trivially simple. 2 of these groups can interact by 2 points of attachment, as you see on top, and the other pair by 3. So it's just a binary system, like 0, 1, 0, 1. We heard about that from Francesca earlier. 1, 0, 1, 0, 1. Here it does 2, 3, 2, 3. And this is enough to process the information which is stored in the genome of living organisms. So chemistry, which is usually defined as the science of the structure transformation of matter, of non-living or living systems, has another property which is very important, which is the science also of informed matter. And this informed matter, the storage is at the molecular level of this information, and the processing is by the way in which they get together, how they recognize each other, how they find out, how they can combine, and so on. Now, this has led then to many, many studies on trying to understand, or let's say, to imitate molecular recognition and to make models and to have artificial ways of creating processes of molecular information. Here you have a cavity, a receptor in white, and you have 3 keys, a purple one, a blue one, and a green one, and of course the purple one is the one which fits. And this has then been developed in many, many laboratories because it's a very fundamental basic process. In our body, all the molecules do what they have to do because they can recognize one another. So without molecular recognition, we would not exist. Our molecules, they do that job all the time. And it's purely physical-chemical. There's nothing magic there. So there are applications, and of course one is especially interested, and the questions come up, what are the applications? Let me just show you some applications of work we have been doing, but there are many other applications. First of all, as I just said, molecular recognition, that's the basis. And that is also the basis of drug discovery. When you make a drug, you can say in Emil Fischer's terms that you try to make a key for a biological lock. a key which you want to build in such a way so that it is as selective. It doesn't make mistakes to bind to something else. Of course, there are always some side effects. And so want to make it as specific as possible so it will just go to its target and then do something, either amplify or repress the activities of that target. So that is the basis of, let's say, developing drugs or pharma industry. We have also made compounds which had a cavity, and you can put things in the cavity. In fact, all of these things, molecular recognition, all have to do with a kind of a target which is more cavity-like and something which can go in. In this case, there was a europium ion introduced in the cavity. When this ion, which is part of the periodic table, of course, when this sits in the cavity, it can emit red light and serve, therefore, as a sort of a bulb, which can be attached to an immunoprotein, which is the surging head, and then you can develop out of that a procedure for medical diagnostics. The machine you see we see on the right is indeed a man, this one over here, which is one which is used now in hospitals and has been developed by Amets. It's a small French company. Now it's a much bigger company. And then the process of leading things through cell membranes is a very important one, because it plays a role in what is called gene transfer. A gene defines a given feature, a given property, and you may if there are diseases where a gene doesn't function well, so you may like to replace it by the one which functions, by the good gene. Or you may want to transform the host by introducing new genes. And that is then genetically modified organisms. And here I would like for all of you to make the strong point that genetically modified organisms are not killing us. Genetically modified organisms, we need them. We need them for making plants which resist heat, which resist drought, when there is no water. And we will use them for many other things, and one can even make genetically modified animals which produce drugs and many other applications. So don't be afraid of genetically modified organisms. They are good for us. I would also like to say a word on some materials and the properties which come out of this type of supramolecular materials. All materials are supramolecular, nothing new. Everything around, a tree, a rock, everything has supramolecular properties because it's an aggregation of different things. But you can then specifically use these features to develop new, let's say, plastics, new polymers. And we did that. And I want just to show you also an example where one appreciates how long it can take to get an application from a basic proposal. In 1990, we proposed in the first paper on that, supramolecular polymers which are constructed on the principles of supramolecular chemistry. Okay, 1990. Then things continued, many people became interested and so on. Then some people thought of making them biocompatible. And indeed, in 2013, I got an email from a small company, I didn't know it existed, telling me that we made from these biocompatible supramolecular polymers, we made implants, a material which can be used for implants for cardiovascular surgery in children. And this company, Xeltis, in the Netherlands, and close to one of the people who has specially developed all supramolecular polymers, Bert Meyer. And so they use this for reconstructing the heart of children who had a very severe cardiac malformation. And I show you now the picture of the first child who was implanted. Here is Dominika, 4 years old at that time, and Professor Leo Bocleria. She was implanted by him, and in a way I haven't time to get into that, on October 23rd, 2013, at the Bakulev Center for Cardiovascular Pediatric Surgery in Moscow. And you look, they both look very happy, huh? The same, so there are many more children than 10 now. And they also, the same company developed also heart valves, which have been implanted also in different, hospitals in Budapest, Krakow, and Kuala Lumpur. And I am told that that is a big breakthrough in surgical practice. Now you see, if you have developed a field, we didn't think about making this kind of things. But it's fantastic, but it took 23 years. And of course, 23 years because you have to put it into a body. And if it's a living body, you have to be extremely careful, so it's very long. And some people, they have the courage to do so, the courage to hang on, that convinced that the idea they have is correct, convinced that one can do it, and then you hang on and you put your shirt on it. Huh? You have to put your shirt on what you want to do. You may not succeed. Another property is that these polymers, because the interactions between the molecules are rather weak compared to the molecular atoms in a molecule, you can make films. Like here you may see a nice film, totally transparent, held by one of my postdocs from India. He holds it, and somebody else cuts the film. Then you cut there. You superimpose the two ends, and you just press with your finger. That was very simple, very trivial, because we just wanted to see if it works. So you put your finger, you thumb on it, you press, and you can then stretch, and it sticks. This takes a minute or two. Of course, you can do it much, much more nicely than that, much more controlled way, but it is enough to demonstrate that it works. And it sticks. So let's come back to the main thread of what I say. After all, the important feature is self-organization. The fact that chemical objects can self-organize, leading to inorganic, to non-living entities. And of course, we are also self-organized. We don't make ourselves. The molecules in our body, they know what to do. They are built, evolution has built them in such a way that they can perform the actions they have to perform, or create the organs, as we just heard a moment ago, the organs from the blueprint, which is the DNA. So let me just show you one example. The first, the virus, which was understood in terms of the way it builds up. It was a tobacco mosaic virus, and it is built of 2,130 bricks, protein subunits, which you see on the right-hand side over there. No, that's not what I wanted. On the right-hand side here, it's difficult to see, but you can see this is a more precise picture. On the left-hand side, it's probably simpler. You have just like a piece of cake, and these pieces of cake, they interact with one another, they go together, and they make a sort of a helix, and in the center there's a hole. In that hole is the genome of the virus, and that happens spontaneously. Again, it looks like magic. Nothing magic. All these processes are understood. All the basic scientific principles on which this can happen are understood. Now, of course, I cannot refrain from calling that a programmed chemical system, and just to let you know that last Monday, the Nobel Prize in Physiology and Medicine it was given for the basic research leading to the messenger RNA vaccines against COVID-19. That is why we are here. Without that, you would not be sitting in this room. You would be at home, we would be confined. And this is science. This is something, and this vaccine was made in less than a year. When it happened, when this pandemic started, I said, okay, now we have it for 8 to 10 years. We have to be very careful and so on. No, we go around. We see each other. We sit together in this room here. And this is thanks to this research done on RNA, which started, something I should tell you. The French government was quite unhappy that no French company had produced a messenger RNA vaccine. Okay. But we should remember or know that in fact messenger RNA was, the Nobel Prize for messenger RNA was given to François Jacob and Jacques Monod at the Institut Pasteur. This is how science functions. You know, there's a discovery being made. This is then a part of the treasure of knowledge in mankind. And then lots of people work on it. Many contributions from all kinds of sides. And finally, because Katalin Karikó and Drew Weissman, they were hanging on to it. They were not sure it would work. And she was almost thrown out of the university. So that's a fantastic story. Hang on. Doesn't always work. Often you can make a mistake and there's zero at the end. But the efforts of everybody, all of people together, lead to things like that. That is why we are here. And of course, one should not forget here that companies are needed. You would not have the vaccines without companies. There was this company in Germany, BioNTech, which is run by two people of Turkish descent, Ugo Sahin and Özlem Türeci. She talked here on Monday, last Monday. And this, so in fact, what did you have? A Hungarian, Katalin Karikó, an American, Drew Weissman, and two descendants of Turkish origin. That is science. You never know where it's coming from. It will come because people are not stupid. They have imagination. There are many intelligent people around the world. There are many courageous people to hang on. And so it happens then. Now, this sort of self-organization which I just mentioned, of course, you can try to reproduce this kind of processes in the lab. I don't want to get into that because it would take a long, long time. But let me just show you some objects one can make by simply taking bricks, which are molecules, and a cementing unit which glues them together, a glue, which are metal ions. So by doing that, one can generate a great variety of architectures, like, for instance, a double helix and a triple helix. They have nothing to do with DNA. What we wanted to do is just to show that one can make double helices by design, by planning it, and then you make it, and then you get a result. And if you get the correct result you expected, then you know you have understood the processes. Pardon. One can also make things like that, like what we call a grid, where molecules are held together in a more or less perpendicular fashion by metal ions which are present at each intersection. One can make this sort of flower-looking one, and we can also make a cylinder where there are linear molecules, flat ones, which are spontaneously going together. There's here, what in all these cases, what you have to do is to design the molecule correctly, and then you just mix, and you get. This is of interest also for nanoscience and nanotechnology. For instance, the ideal would be that this type of computers, which is here, this you have to make it. But well, maybe in the future it will make itself by assembling, spontaneous assembling. And there is a good example for that, which will convince you. The most powerful computer still around is our brain. That is why we understand all that. And you don't make it. It's make itself. You don't have to put it together piece by piece. It makes itself because all the processes are there which can lead to it, and it has evolved in such a way. Now, just one word about what we are now interested in. For the moment, I told you about designing objects, putting information, molecular objects, programming the system so that it will have a given architecture, which is a given function, which you want to put into it. Beyond that, there is another property which we can introduce, which is what about letting the system choose what it needs to build itself up? And this is done with selection, selecting the correct bricks from a diversity of bricks. So you need many diverse bricks, and you need also what you may call dynamics, so that when objects get together, the first collision, if it is not the best one, best meaning for a scientist, thermodynamically the best one, then it can separate again and look for something else, so that it can sort of adapt, it can optimize the final result, the product. This leads to an adaptation of the system to, for instance, changes in physical agents. If you change the temperature, you put the pressure, you add something else to it, the system may change and respond. And we call that adaptive chemistry. Yeah, chemistry where the objects are able to adapt to changes which occur and adapt to different kind of agents which come around and so on. And it can also be used for developing methods for discovering biologically active molecules and for materials and so on. I haven't time to get into all that. So the evolution of chemistry therefore starts, of course, atoms before, but once atoms get together, they make molecules. Then you have the supramolecular effects when molecules interact with one another, like in our body, organized, okay, they have a given organization, which is preferred compared to another one. The dynamics are important, so as not to have something inert. If it's inert, very little chance that you will optimize further. Then adaptive, evolutive, and this is more towards more and more complicated, complex features like those happening in life and in thinking. Thinking is much beyond even life. Life is a simple problem compared to thinking. So let me summarize. You understand that I am, of course, I think I'm first of all a scientist. I try to be one. But considering chemistry, you have understood that chemistry is a creative science also. As I like to say, the book of chemistry has to be written, not only to be read. Of course, we have to read the book of compounds developed by nature in the course of evolution, trees, plants, flowers, animals, and so on. But there are many, many, many combinations which have not been made, and this is to be written. Similarly, also the score in musical terms of chemistry has to be composed, not only to be played. So chemistry can be considered to have creative power like art, and chemistry is the art of matter, the art of making new combinations which did not exist before they were done. This has already been said in other terms, of course, and in other circumstances by somebody all of you know, Leonardo da Vinci. He was an artist, he was a scientist, he was an engineer. And he wrote a very fantastic sentence in his times. I think he probably, had he written that 100 years earlier, it would have been burned. Where nature finishes to produce its own species. We are part of that. We are part of the species generated in the course of evolution. Man begins, of course women too, using natural things. Natural things, what are they? The bricks of the periodic table of elements. The bricks which are at our disposition, the bricks which have been generated by our universe. This is what are the complex objects, molecules, and so are made of. In harmony with its very nature. That means just the laws of physics. You cannot get around it. Like when you play a game, you have laws, and you apply those laws, and they determine what you are allowed to do or not allowed to do. And then the end of it is a very, very strong end, because Leonardo was an artist. And for an artist, creating something is a very, very strong term. And he did not hesitate in saying to create an infinity of species. Some people at that time, his time, they were saying, this guy is crazy, you know? To create, who dares to create? There's only some people think that creation has appeared somewhere else and somewhat differently. To create an infinity, which is true, of species. Very strong statement. So it's not just the natural things we have to worry about and we have to be interested in, but what we can do. Coming back to the mythology of Greece, in Greece. Here you see Prometheus, which has stolen the fire of knowledge, again, knowledge, from the gods. And he looks over his shoulder, running away to see if the other guys are not trying to catch him. But they didn't catch him, and he gave it to mankind. And here you see another Prometheus showing the fire in question, the fire of knowledge and of science. Now, a very important consequence we must realize is that we cannot give it back. What you know, you know. You cannot just erase it unless you destroy the planet totally. That's an option. But there's certainly on other planets there will be other people a bit more intelligent who will not destroy themselves. So we cannot give it back. What does that mean? It means that our path leads us from the quest of knowledge to the control of our destiny. Evolution is now in our hands. We can make humans evolve, let's say, artificially. But one has to be very careful. I don't say that that's a very complex problem, but we will have more and more the power. And when we heard about stem cells by Yamanaka, you can, in a cell, all the information, the DNA is there, so everything is there. You just have to know how to use it, and you have to define how to use it, in which conditions you want to use it. These are fantastic challenges for the future. It will be not easy to know how and what to do, but we have the power to do it better and better. Not yet all of it, but better and better. So let me finish with a mathematician. I haven't seen much about mathematics. In fact, very little. Here is David Hilbert. He comes also from a university, that small city of Göttingen. We heard about Göttingen before. Göttingen was quite a good record in advances in science. David Hilbert, he wanted to have 2 sentences written on his tombstone, and when you go to Göttingen, you see that. The first one is, wir müssen wissen, we must know. That was drives scientists. This drives us. We must know. Come on, we must know. The second statement is even, I would say, stronger because it's a vote of confidence. We must know. Wir werden wissen. We will know. That's a word of confidence. And of course, if you are driven by this push to know, at least you must have some hope that you will know at some stage. So here is again Prometheus holding the light of science. We will know. And for the younger people in the audience who have still their future to make, and also for the others, science shapes the future of humanity. I advocate that if you go to the beach and do some swimming, or you go to a tennis court and do some tennis, okay, that's fine. But I think everybody should spend some time every week to get to know more about science, because our future depends totally on it. So there's this passion for knowledge, and because there is this passion for knowledge, I think mankind has a good chance, although we are not certain, to know more and more, to be able to control itself better and better. And there is finally another property which science has, and which is only science has that property. Here is our piece of dust in an enormous universe turning on itself. We are sitting on that ball, and we are nothing in the universe compared to the immensity of the universe. But the creation of science, developing science, makes us all brothers, not just around the earth, but if we meet some other organism somewhere else, water, alcohol, benzene, and all these things will be the same. So science has no borders. Science has no borders between people. Science has no flags. Science has no dogma. Science has no politics. Science is the only activity of mankind which spreads all over and which is valid not only on our planet, everywhere. Thank you.
Thank you so much, Professor Lehn.
Tira, honekin amaitu dira gaurko hitzaldi nagusiak, baina gu ez goaz, senyora, Bertso Passion saioaz gozatzeko aukera izango dugu jarraian.
Passion for Knowledge jaialdiaren edizio honetan ere, bersolari honetako batzuk bildu ditugu berriro, gure zentzumenen gozagarri. Zientzia gaie esarituko dira noski, eta ziur gaude punta ateratzen moldatuko jasmatuko dutela.
Gu ez gara azalpenetan luzatuko, badakigu beraiek entzutera etorri zaretela, beraz, datozela Amets Arzallus, Andoni Egaña, Maialen Lujanbio eta Nerea Ibarzabal bertsolariak.
Eta Gai-jartzailea, Maite Berriozabal izango da, eman diezaiegun merezi duten ongi etorria.
Arratsaldeon denoi, ez dakit goian norbait badagoen ilunetan, arratsaldeon ala bada. Arratsaldeon eta eskerrik asko saio hau horren jardunaldi interesgarri eta guretzako jakingarrien parte egitearren. Edarra da guretzat hemen egotea, eskerrik asko antolatzaileei. Eta eskerrik asko zientziak edo bertsoak ona ekarri bazaituzte gurekin tartetxo hau pasatzeko autua egin duzuen guztioi. Luzapen askorik gabe aurkeztu egingo dizuet gaurkoan kantura etorri den laukotea, eta ertz hartatik hasita Amets Arzallus. Andoni Egaña. Maialen Lujanbio. Eta Nerea Ibarzabal. Eta zientziaz ez dakit, baina hitzez, improvisazioaz eta hizkuntzaz zerbait badakite. Eta hasi egingo dara guk gure egituratik, gure esperimentutik, hasieratik, zatozte agurbana kantatzera.
Kaixoz esango dugu guk zuen jarraian, zenbat izar zeruan ta argi sabaian. Gure teoriekin ez hasi ez baian, gehien kantatzen dugu ez dakigun gaian. Beti gure burua deskubritu nahian.
Gonbidapena luzatu zuten, eta nola egin uko. Baina urduri jarri leike bat, Nobel sariak gertuko. Goizean amak ala esan dit, egoeraz jakin orduko. Barrengo erropan imagina hitzak, eta ez aiz beldurtuko. Gabon talasai aman esana, gaur ez dut aintzat hartuko.
Bertso Passion zientzia eta hitz, nasketa kuriosoan. Zer da gure hau, puska bat gazi eta puska bat gozoan. Tanta bat bihotz altxagarria, tanta bat deserosoan. Gramo erdi bat ingeniota, ausardi gramo osoan. Formula baten kabitzen ez den tximista bat da bertsoa.
Arratsalde hemen gatoz bost, partikula inestable. Bost adimen ez hain artifizial, bost teori kuestionable. Gu bapateko hitzekin eta hemen ze jakintxu talde. Baina ikasteko beldurrez denak lasai egiten du galde. Kanta dezagun jakin minaren eta zalantzaren alde.
Hurbildu mesedez, Amets eta Andoni. Behar bada handik edo hemendik komunikabidetan, irakurriko zenuten Euskal Herriko Unibertsitatean, da beste unibertsitate batzuetan ikerketan ari diren hainbat doktore gaik edo doktorek, basalatzen dutela oso diru sarrera txikiekin egin behar dutela lan, hor askotan diru laguntza publiko bat, izaten dute 800 eurorekin bizitzera behartuak. Ikusten direla aipatu dute eta azken aldian horri boza eta protesta erantzi zaio. Eta hortxe kokatuko gara, zuek biok zarete ikerlari, biokari zarete unibertsitatean doktoretza egiten, eta zuk, Andoni, 3 urte daramatzazu dagoeneko. Amets hasi berri da, eta Ametsek esan dizu, nola egin dituzu 3 urte? Nik nahi nuke, baina ez dakit halko dudan.
Ene berria zaitugu Amets, ta galdezka berehala. Ondo dakizu zenbatekoa, dan guk daukagun jornala. Ia nolatan irauten dudan, bi hitzetan nola ala, eta eskerrak nik bikotea, funtzionarioa dedala.
Diesela 2 euro eta kaina 4, 100 gaueko zenbait txuten. eta alokairu bat Donostin 1.200 truke. 800 euro kobratu hemen daramatzazula urte. Ez dakit hori ikertu duzun, nik formula nahiko nuke.
Hiru urtetan 800 euro, gutxi dugu ala fede, bizi moduan moldatu behar, ezinean ta xelebre. Esaten zuten fakultadean, eingorantza oso trebe, baina sabai bat badago hemen, gizonezkoentzat ere.
Gizonezkoek beraz, sabaiak ta ezin hautsiz besoak. Kimikan fuerte saiatu nintzen, arixe jarriz bersoak. 4 master eta 3 Erasmus, ez ziren izango xoak. Berso eskolara joan zirenak, ez ziren hain inozoak.
Nik 3 urte badaramazkit, lanean ta beharrean, ohartu zaite sartuko zera, hain egoera txarrean. Naiz hasieran egon zintezken, ikarazta beldurrean. Manifaren bat egin behar dugu, rektoretzaren aurrean.
Egin manifata jarri zaite zeu kartel horren atzeko. Ia etxi dute zindut segi zu hor zabiltzan antzeko. Donostin ez dut itxaropenik nik bizitza salbatzeko. Voluntario aurkeztuko naiz ilargira bidaltzeko.
Etorri orain beste biok, Maialen eta Nerea. Zientziak bereak ditu tituluak, bertsolaritzak ere bai. Esan dezagun Euskal Herriko txapelduna bada Maialen, behar bada Euskal Herriko bertsolari nobela sariduna izango litzatekela, edo Nerea Bizkaikoa, halaxe da. Bertsolaritzan ere beste leku askotan bezala jarduna publikoa da, aritzen zarete plazaz plaza, eta gauza jakina da geroz eta emakume gehiago dabilela plazan, zuek zarete horren adierazgarri. Emakumea beste alorretan ere badago, kulturan, zientzian, kasurako, baina egiturak gizonenak izaten jarraitzen dute egiturek. Zuek jarduten zarete, geroz eta gehiago zarete, geroz eta biztarago zarete, baina oraindik ere munduak, egiturak gizonena izaten jarraitzen du.
Aldatzen zaio azala baina mantentzen zaio eskema. Gukurratu nahi dugu oinarri hortan bide bat ez dena. Berdin txapela, berdin nobela, gauza arrunta ez dena, gizonentzat da orea eta andrentzat salbu espena.
Beraz kostata sartuta ere bertsoaren elitean. Oraindik batzuk zentruan eta besteak satelitean. Oraindik ere saio batean kantuari ekitean. Sarri gizonai behatzen zaio dirua zitz egitea.
Gu gizonekin goazenean gizona da nagusia. Gizonena da ordutegia ta bertso saio luzia. Gizonena da dema itzena ta umorearen auzia. Eta gu hitzez saiatzen gara iraultzen hori guzia.
Eta eskerrak agertu zinen garai baten holtzetan. Neska guztiok pentsa genezan egon nahi nuke hor bertan. Alere sabai ikusezinak beti dauzkagu kopetan. Baina kantuan jarraitzen dugu bekokitiko odoletan.
Baina esaldiak dion bezala egin borroka ta suen. Nik bezelaxe gazteagoek lan alatze egin duzue. Ta emakumeok feminismoa kantagai dugu aizue. Seguru asko nekagarria gertatzen ari zaizue.
Feminismoan mila aldarri aizatu izanaren truke. Hemen batzuek isiltasuna agian nahiago dute. Baina galdetuz oin dituztenei 17-20 urte. Euren adinean neuzkan arazo berdin-berdinak dituzte.
Etorri, Andoni. Zientzian aritzen eskaenok zientzia pentsatuta ez dakit. Batzuk izki batzuk, beste batzuk behar bada laborategi bat, beste batek zenbaki pila bat, izki batzuk. Eta zuri gaur zientzia etxera heldu zaizu, zelan baita esateko, posta ireki, eta gutuna sal bat, zure izen abizenez, zigilu bat ezagutzen ez duzun institutu batena, ireki duzu eta gutuna sal bat dago, gutuna sal bat. Eta izenburuak hala dio, bizi nahiko zenuke betiko, eta behan jartzen du, aukeratu gutxi barutzuk izan zaretela, halako esperimentu baten parte hartzeko, eta parte hartu ezkero, oso posible dela, zientziak aurkitu duela modua, betirako bizitza hori bermatzeko. Zeure esku dago orain, bizi nahiko zenuke betiko.
Adarra joaz hor dabilzkit nik, atzetik hainbat aseri, honek broma bat izan behar du, ta eser nadin eseri. Bizitza zenbat luzaliteken, gaur egun mila komeri, zergatik egin behar genuke, segi, 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 bizitzak beti iraun behar du, ez gutxigi, ez gehiegi. Bueno, urte batzuk hartu nahi ditut, enaiz alako txepela, 85, 90, hori da nere nibela, eta aldala izan dadila, bizitza bete itzela, zergatik beti argirik gabe, ikusi gure tunela, nik pentsatzen dut hasten den orok, bukaera behar lukela. Esperimentu baten parte hartu, neretzako ez da traba, baldin aukera sortu bazaigu, albora zergatik laga. Orainak aso heldu ninteke, 7.000 urtetara, tanik mundua jasan dezaket, garbi esango dut ara, baina ez dakit onar liteken, alderantziz baldin bada.
Etorri orain beste hirurok, Amets, Maialen eta Nerea. Nik uste dut oso gutxitan izendatu direla bertso saioak horrela, eta hau da Bertso Passion. Niri polita iruditu zitzaidan, Passion, pasioa. Jarri egon pasioa apur bat kontuari ez da. Zu Nerea pasio handibi dituzu. Bata da Maialen eta bestea da Amets. Amets da zure bikotekidea, eta Maialen da zure txakurra. Dira zure bi pasioak, eta nahi dituzu biak, eta asko gustatzen zaizu biak aldi berean. Hori are pasioa. Kontua da, Ametsek gorroto duela zure txakur, Maialen. Eta Maialen zure txakurrak gorroto duela Amets, zure bikotekidea. Gaur ere, arratsaldero iluntzero bezala, telebista piztu eta hirurok zaudete sofan.
Nerea ja filosofikoki hasi behar dut galdean. Nolaz daukazu lau hankako hori bi hankakoen parean.
Maite zaituztet maila berean ta orekatuan berez. Berak sofa hilez betetzen dit ta zukoean baterez.
Sartu nazazu zure ondora eraman zure mantara. Behatzak zupatuko dizkizu tipori joaten bada.
Zure mingaineko germen hoiek naukate izutu xamarrik. Berak ere miazkatu izan nauta ez behatzak bakarrik.
Karlino itxusi horrekin nun nahi egiten dut estropozu. Nundun aurrea eta nun atzea antzematen aldiozu.
Ba neukere galdera horretan sarritan ez dut jakiten. Sarri begira egoten naiz jana nondik sartu nondik irten.
Horraz nazazu zenik melena daukat korapilatua. Ni pedigriko txakurra naiz ta oikalean bilatua.
Baina pozoia duzu barruan ta igual ariman sarna. Zaude isilik erungo zaitut albaitariaren gana.
Karlino horrek noiz nahi mingaina lerde jario du ara. Baina Nerea ez da zugatik transpiratu ezina da.
Baina gure arteko maitasunak ematen ditu pausoak. Ez dakit tximeletak ditudan edota arkakusoak.
Ez baduzu nahi tiporrekin zure harremana bukatu. Neri emaidazu jakiona eta zuek ezurrak txupatu.
Bakoitzari eman beharko zaio tokatzen zaion partea. Katu bat ekarri beharko dut eta biontzat bakea.
Nerea guztia argitzen da euskarak duen klasian. Nerekin asezazu pasion horrekin joan pasian.
Pasioa ere 10-12 urtetan honi akabo. Gure harremanak edo txakurrak zerk iraungo du gehiago.
Hau triangulo imposiblea da naiz eta zulotzen ari. Arkatuei alergia die eta nik berriz berari.
Baldu dira adiskidantza, sina dezagun sasoiak. Mozalbana erosiko dizuet eta niretzat tapoia.
Etorri, Maialen. Zuk beti nahi izan duzu bizitzan zerbait importantea egin. Eta importantziaren bidea bilatu duzu gauzak asmatzen eta patentatzen. Eta asmatu dituzu gauza pila bat. Eta patentatu ere bai, eta diru pila bat gastatu zu. Eta oraindik ez da iritsi zure ospea eta zure arrakasta. Etxea trastez beteta daukazu. Oraingo honetan ere pentsatu zenuen, hau bai, oraingo honetan bai, asmatu dudan honek mundua aldatuko du eta ni egingo nau benetan ospetsu, nik nahi nuena. Eta patentatu duzu halako entzungailu batzuk, aurikular batzuk, neguan beroa ematen dutenak belarrietan. Eskatu zenituen 100 bat, 200 bat, behar bada 1000 kaxetan dituzu etxean. Asteak aurrera doaz, eta jarraitzen duzu zure ez dakit zenbagarren patentea, zure ez dakit zenbagarren asmakizuna, zure entzungailuak, eta zu.
Galtzerdi batzuk 5 behatzdunak, ta inoretzegoen aurka. Gero bizkarra azkatzekoa asmatu nuen zemauka. Aurikularrak gero ondoren, taniarekin flipauta, gainera bero ematen dute, ni neguak osten nauta. Bombak asmatu zitunak baina, arrakasta gehiago dauka. Otordutako makinatxo bat kozinatzen duna bixi. Bi elementu kombinatuta sortzen da 1000 kutixi. Oinetakoak bikurpildunak alperrentzako justizi. Eta katu bat eiten dizunak kejatu gabe karizi. Baina munduan nahiago dute lengo txar denekin bizi. Betaurrekoak katale jodun, jartzeko begien jiran, edo erropa bonbiladuna, gauez joateko diztiran. Mundu berriak beti ego naiz inventatzeko desiran. Pentsa betiko bizitzan klabe ezkutua daukat nigan. Baina hori ere Andoni Egañak errefusatu egin zidan.
Etorri Nerea eta Andoni. Nerea, zuk ordu asko pasa dituzu Andoni sortzen, Andoni eraikitzen. Eta Andoni da sistema bat gaur egun inteligentzia artifiziala buruz asko dakizue, gaizki esandakoak nahita dira. Hortan oinarritua dago Andoni, eta Andonik daki momentu jakin batzuetan guk baino gehiago. Zuk sartu duzu informazioa eta Andonik lotzen ditu informazioekin da gauza asko dakizki. Kontua badakizula sistemak baituela akats batzuk, baina bilatu egin behar dituzu. Nola bilatzen dira akatsak? Zen mailatan daude akatsak? Bueno, pentsatu zu hasiko naiz errazenetik eta joango naiz zailduz ikusteko non sartzen duen akatsa, non sartzen duen hanka Andonik. Beraz, hasiko zara Andoniri galdetzen, Andoni hasiko zaizu erantzuten, eta ikusiko dugu ea Andonik dena dakien zuk diseinatu zuen bezala, edo badauden gauzak Andonik ez dakizkienak.
Nola bereizten dira gaua eta eguna.
Eguna izaten da argi gehioduna.
Eta Frantziak zein du bere kapitala.
Oraindik ere uste det Paris duala.
Zarautzen zenbatean dago alkilerra.
1.200 eurota sortu den gerra.
Zenbat txapelen jabe Andoni Egaña.
Launa bakarrik 5 nahi zitun baina.
Ta egunean zenbat zigarro erreditu.
52 naiztazu harritu.
Ta zenbat fisikari daude Donostian.
Asko topa litezke harrien azpian.
Ta pasioa zerek pizten dizu zuri.
Ez dut esango ni zerk jartzen naun urduri.
Noiz desagertuko da mundutik euskara.
Denbora luzean gu euskaldun gara.
Azken galdera hortan zalantza egin duzu.
Euskerarena ziur espaineukan aizu.
Eta aske izango alda inoiz persona.
Hori litzak helburu edertasakona.
Noiz dator 3. Gerra Mundiala.
Uste dut bihar goizez hasi behar duala.
Ez zaude apurtuta nahiko ondo zaude.
Ara ze ondo nabilen entxufatu gabe.
Etorri Amets. Zindagit aurretik ez dizkidala gaiak kontatzen, baina Amets konektatuta egon da nonbait. Ez diote inori ematen halako lanik eta halako ardurarik, zeuri eta bakarrik zeuri eskatu dizute, urte luze batez jendea ezagutzen, jendea elkarrizketatzen egon, eta gero, ilargirako bidaian zein joango den zurekin bidelagun erabakitzea. Hemengo dano kanpoan gelditu dira, sentitzen dugu, diru hautagai baino ez dira gelditu, Andoni, Maialen eta Nerea. Bakoitzak bere hautagaitza saldu beharko dizu, izan ere ez dago edonoentzat tokirik, leku bakar badago, zurekin batera, ilargira eramango duzun, pertson hori aukeratzeko tarte orain.
Ilargiraino bidaiatxo bat, ez negoke horren kontra. Alare joan edo ez joan ez zait askorik inporta. Orain suplente utzi nazazu, beste bioiekin konta. Urrengo baten joango naiz ni sekulaen aizilkota. Urrengo baten joango naiz ni sekulaen aizilkota.
Poza hartu det ikusirikanik Andoniren eskua. Hau da gizon bat oso jakintxu, gizon bat oso prestua. Egunean 40 dukados, pentsa zeharnaz aurreztua. Honek tabakotan botako du nasaren presupuestua. Honek tabakotan botako du nasaren presupuestua.
Bertsolaria izan nauzuni, holtzakoa eta maikoa, beti sakona igual iluna serioen bisaikoa. Dramatismo handiz kantatu oidut nik garaian garaikoa. Grabedaderik ez badagoan neonek badet nahikoa. Grabedaderik ez badagoan neonek badet nahikoa.
Grabedadea baduzu nun baita horixe ez da traba, baina zer horren hautagaitza hori beharko zenuke traga. Askotan jardun gara elkarrekin, neretzat txarra da ara, zezu lehenago helduko zara biak joaten bagara. Zezu lehenago helduko zara bio joaten bagara.
Nik ere zerbait egin nahi nuke, astronomian karreran, eskolan behintzat trakets samarra nintzen horretan aukeran. Esan zidaten non bizi zara, ilargian edo egan, ea behingoan neure burua antxe topa dezakedan, ea behingoan neure burua antxe topa dezakedan.
Beraz beti erdi ilargian omen zinen zu aritu. Zure janzkera ikusi eta ez dut ala nabaritu. Biok joan eta aizen notizi mundu osoko prediku. Nerea joan ta ilargia itzali zen ta bera berriz argitu. Zu joan ta ilargia itzali zen eta nerea argitu.
Zientzia ere bada sormena, edo zientzia sormena da, behar bada. Eta gaur nahiko genuke zubi bat eraiki, alik eta literanena, zientzia eta bertsoaren artean. Eta zer egingo dugu? Bertsolariak sufriarazi apur bat eta guk ondo pasatu. Beraz, talde bi egin ditut nik. Batetik daude Amets eta Nerea, da talde bat, eta beste talde bat Andoni eta Maialen. Eta dena ez denez nire esku geldituko, aukeratu ditzakezue bi gauza. Bat da, ze talde hasiko den, zeinek hasi nahi du. Lehenengo aukeratu da, bigarrena ezin da. gu, Amets eta Nerea. Txalo bero bat. Eta lehenengoak izan zaretenak eta ausartenak aukeratu ezakezue ze ariketa egin nahi zuen, ze desberdinak dira. Bai? Bertsolaritzan ere eta munduan askotan gertatzen da, bakarka egiten ditugula gauza batzuk, baina bakarka beti ez da errezena. Orduan, ariketa baten izena da, bakarrik ezin da, hori da ariketa bat, eta bigarrena da, zientziak batzen gaitu. Pista batzu daude izenburuetan, bakarrik ezin da, zientzia batzen gaitu. Bale, aurrera. 3 bertso eraiki beharko dituzue, 3 abanera, eta zientziak batzen gaitu eragiketa matematikoak. Ulertu behar zenuten, ez duzu ikusi izenburuan. Batzen gaitu, eragiketa matematikoak egingo ditu. 3 bertso eraiki beharko dituzue. Batu sari garen ez, bat ez bada bi, ez? Orduan, 222 bai? Orduan, eraiki behar duzue, bide bat, 222raino. Bide hori, bertxotan, zuek nahi duzuen eraiketa motekin izan daiteke. Batu izan daiteke, kendu izan daiteke, zatitu izan daiteke, biderkatu, edo ez dakizkigun beste gauza horiek. 3 bertxotan, hori, 222 arte, baina gutxienez 9 eragiketa. 3 bertxotan. Hortik gora, plus. Hortik gora, plus. Osea, egiten behituzu denak bat, bakoitzeko eta bestela plus.
Bat gehi bat bi izango da, ezer aldatu ezpada.
Ta bi bider bi lau dira, hori ez da harrikada.
4 gehi 7 11 ez da, nahasten hasi naiz jada.
11 eta 7 18, 8 eta 1 euskara.
22an algoaz, hau da, hauxe matxina da.
22 nork esan du aizen pilotaka da.
Erabat galdutanago sartuz matematikara.
Gehitu Donostin Laukaña eta ja iritsi gara. Ta gehitu beste 3 pintxo Laukaña hoien ondora.
Baina aterako zaigu 2000 eurotik gora.
2000, 4000 dira joan ezkero Bilbora.
Poteatzen dugulako kale hauetan gustora.
Uste nuen batzen gaitu hori zela metafora.
Infinitua ari zait ja bilakatzen denbora.
Nik aspaldi utzi nuen matematikaren droga.
Egia esan bide hortatik ez ginen heldu inora. Bueno, 100 goaz, eta orain hortik gaindi.
Beste 40 gehitzeko eskaiozu Egañari.
Egaña hortxe ari da kalkuluekin errari.
Egañan adina gehitu ta ia 300 adi.
Baina gaur lortu duenez eternitatea sari.
Ta bider Maialenena, ja 300 atari.
Hementxe juntatu dira beraz Troiako bizaldi.
Kendu 78 ta
222.
Bueno, zuek esango duzue. 4 puntu edo, 18raino, eta gero 100, eta gero 300, eta gero 222. Venga, ba, 6 puntu, txalo bero bat. Etorri orain Andoni eta Maialen. Zuena da bakarrik ezin da. Gau, tokatu zaizue pixkat letretagoakoa dena, Bakarrik ezin da. 2 zenbakia, leku askotan dago. Galdera da, zenbat gauza bizitzan dira 2? Zuen kasuan da plus, gehitzen baduzue, zenbat gauza bizitzan dira 4. Bai? Zerrendatu, zenbat gauza bizitza diren 2, eta tartean plus nahi baduzue, erresamarrutzi dizuete, behar bada 2rekin nahikoa da, plus zenbat gauza bizitzan dira 4.
Bi begi ta bi belarri, atera ezkero kontuak.
Bi esku eta bi hanka, ditu pertsona osatuak.
Biz bukaeran askotan, ipintzen digu kantuak.
Dena egiten du binaka, gizarte bikotetuak.
Binaka dentrifiko bat, aspalditxoan sortuak.
Ta 4 anuntziotako famili hain perfektuak.
4 errege badaduzka, euki musaren jokuak.
Ta izatekotan bidira, beti arrautza prejituak. Bidira antonimoak, nola gauak ta egunak.
Bidira ia gauero, komunerako jardunak.
PNV eta Bildu, etxaiak eta lagunak.
Batzutan alderdi baitan, sortu litezken bildumak.
Kolakautan eskuik ere, binaka dauzka garunak.
Sarritan bizaten dira, ez konkide eraztunak.
Bi ikusten dut dendena, gehiegitxo edandunak.
Ta bi gol ederrak atzo, realak sartu zitunak. Moskor batek ba espare, bizpere esan dezake.
Bi aldiz errepikatzen dira batzutan hitzake.
ETB bi jasatea, ze perezata zeneke.
ETB baten birritan dena emanda daukate.
20. mende hortan mundukoak 2 gerrate.
2 aldiza osapaian janak eiten badu kalte.
Sarrerako eta irterako hemen dauzkagu 2 ate.
Ta hemen bikotea askok 3ko forma daukate.
Hogeita lau, B+, txalo bero bat. Eta pentsatzen duzunean nahikoa sufriutu dutela, bertxotan jarraitzen dute, baina oraingoan librean, zatozte tartetxo batean zeuenak esatera.
Putzura bota daigun zientziaren giltza, zientziaren giltza.
Zientzia arte honetan arraro gabiltza.
Jakin gabe kantatu ze ofizio itxa.
Ze komplejua izan daiteken bizitza.
Eta itzultzaileak zer moduz dabiltza. Eta itzultzaileak zer moduz dabiltza.
Gaur ze saio zaila zen, ez leike kalkula, ez leike kalkula.
Espainolez aitzen da zeo zer xuxurla.
Dardarka baitze euskaten 11 zelula.
Kontuz Andonik dakar azken formula.
Asko antzeman alda deus ez dakigula. Asko antzeman alda deus ez dakigula.
Bada pentsa guk ere sariak dauzkagu, sariak dauzkagu.
Hemen buru bakoitzak txapelen bat badu.
Ta hoie kontatzea izan arren tabu.
Oraindik jende honek lehiatzen diardu.
Ta gure nobelonek Oskarran antzadu. Ta gure nobelonek Oskarran antzadu.
Hemen denonak dira garun espezialak, garun espezialak.
Ez da erresa ongi gainditzen oialak.
Batzunak gizenak eta bestenak argalak.
Gure hitzak dira euskaraz internazionalak.
Aldarrika ditzagun zientzia sozialak. Aldarrika ditzagun zientzia sozialak.
Nobel zan dinamita asmatu zuena, asmatu zuena.
Beraz haren kulpakin txikitu zen dena.
Bistan da Wikipedia beiratu duena.
Ta Oppenheimer berriz atomikoena.
Denen aurrean esan behar nuen nekiena. Denen aurren esan behar nuen nekiena.
Dinamitaren hori ez genekin tira, ez genekin tira.
Beti ikasten dugu ametsi begira.
Zerbait lertuko alda hemendik gutxira.
Bakearen novela bastante bitxi da.
Baina aktibatzeko 2 metxa behar dira. Baina aktibatzeko 2 metxa behar dira.
Teknologian txarrak geragu alare, geragu alare.
Naiz eta danok izan mobil baten jabe.
Bi aldiz kantatzen dugu hementxe goitabe.
Eta bistan dagonez gu galduta gaude.
Ponentzi bakarra zen PowerPointik gabe. Ponentzi bakarra zen PowerPointik gabe.
Beraz ointxe zapaldu du egunak gailurra, egunak gailurra.
Beririz ere hartzagun lengo bide txurra.
Hemen azaldu dugu dakigun apurra.
Azkenera llegatu gara purra.
Mil esker denagatik hauxe azken agurra. Mil esker denagatik hauxe azken agurra.
Zuek bidaltzera gatoz, non bait? Bueno, zeinen ongi ezkontzen diren zientzia eta bertsolaritza, baiet, Javier?
Bai, hoxe, Passion fornalitzen maite dugu kultura disiplinen arteko fusioi.
Bueno, gaurkoz amaitu dugu, guk bezain ongi pasako zenutela espero dugu, eta gustu baduzue, bihar ere hementxe izango gaituzue arratsaldeko 6-etatik aurrera. Eta nortzuk izango ditugu gonbidatuak? Entzun Joakin Gorrotxategi, Irulegiko eskua ikertu duen hizkuntzalaria, Jak Sostak, zahartzea eta bizitza artifizialari buruz hizketan, eta elkarrizketa interesgarri bat, Pedro Miguel Etxenike eta Jocelyn Bell Barnelen artean.
Y después de las conferencias plenarias, a las 8 de la tarde, un último apunte, podremos disfrutar de Naukas Passion, un formato compuesto por charlas cortas que combinan la ciencia, el escepticismo y el humor.
Nosotros no nos lo vamos a perder, así que les esperamos.
Eskerrik asko, Villar arte.